conectados con la mesa. Arriba está encendido y para abajo está apagado.
Vale, entonces... Vale, eso. Hello everyone, we are going to start this midterm conference of the Maxima project. Thank you all for coming here, and we have this event live in YouTube, so hello to our audience there too. We have a live chat, so you can ask all the questions in YouTube. And let's start this midterm conference of the Maxima project. We have the welcoming words of Feuga General Director Javier Pereiro that is going to give you the welcome to this event and to Santiago. So let's give the floor to Javier Pereiro.
Well, good afternoon, distinguished guests, esteemed colleagues and valued partners. As Managing Director of Feuga, it's an honor to welcome you to Santiago de Compostela and to the headquarters of the Feuga Foundation for the midterm conference of the Maxima project. Today we are there to assess the progress of this ambitious initiative, which has the potential to transform the automotive sector in Europe and consequently make a significant impact in Galicia as well. The automotive industry is a key pillar of Galicia's economy. In 2023, the sector reached the record turnover of 13 billion euros, marking a 12% increase compared to the previous year. The industry employs approximately 24,000 people, accounting for 14.8% of Galicia's industrial workforce. Additionally, our region produced 22% of the cars manufactured in Spain, surpassing other important hubs like Martorell or Pamplona. Exports in the automotive sector reached 9.4 billion euros in 2023, a 14% increase for 2022, representing 31.3% of Galicia's total exports. These figures highlight the strategic importance of the industry for our region's economic growth and innovation ecosystem. A fundamental driving force behind this success is the role played by key industry actors such as Feuga, Galician Automotive Cluster, and Stellantis, both of whom are esteemed trustees of the Feuga Foundation. Stellantis, as one of the leading manufacturers with a strong presence in Galicia, continues to drive industrial growth, employment, and technological advancement in the region. Their contributions are instrumental in shaping a sustainable and dynamic future for the automotive industry. In this context, Feuga's works become increasingly relevant. As a bridge between research, industry, and technological development, Feuga plays a crucial role in fostering innovation, facilitating knowledge transfer, and supporting the transformation of the automotive sector toward a more sustainable and efficient future. The transition to electric vehicles is crucial for reducing greenhouse gas emissions and combating climate change. EV motors not only offer higher energy efficiency, but also require less maintenance and provide instant torque, enhancing both performance and driving experience. The Maxima project is at the forefront of this transformation, developing sustainable and high-performance electric motors that align with global efforts in decarbonization and sustainable mobility. In addition to the technical discussions and collaboration opportunities that this event provides, I encourage you to enjoy Santiago de Compostela, a city that blends history, culture, and a warm and welcoming spirit. As the home of the Camino de Santiago and a UNESCO World Heritage Site, Santiago offers a unique setting that will undoubtedly enrich your experience during this conference. I invite you all to make the most of these days of work, knowledge exchange, and networking, with the shared goal of driving the future of the automotive industry forward. And of course, if you have some time available, I invite you to enjoy the carnival celebration and festivities that are being held nowadays in Galicia. So welcome and thank you for your participation.
So thank you again, Javier, for your kind words. And now we can start with the technical presentations of our conference. We have now the floor is to our project coordinator, Stéphane Clenet, for Arts-et-Métiers Institute of Technology. He is going to introduce the Maxima project, objectives and the goals we are working towards. And he is the person who is going to introduce the next speakers of the project consortium that are going to explain how the project has advanced to this term, like this midterm event. So welcome to Stéphane Clenet.
So thank you, Angela. So thank you, Javier, for the organization. So I would like to thank Feuga for the organization of this midterm conference. It's a real pleasure to be here. And until now, what I should say is that the meeting we had this morning was very well organized and very profitable. So I hope that the conference will also be on the same way. So I would like to present an overview of the project Maxima before going deeper in a technical aspect. So, okay. Sorry. Okay, thank you. So just about the general context, so it has been said just before by Javier. In fact, we have a massive electrification in automotive. So it means that if we want to develop such kind of electrification, we need to manufacture or to construct, to design vehicle accessible to everyone. So it means that we have to manufacture at low cost. But in the same way, in parallel, we have also to develop a system or devices that have low environmental impact. So what it means? It means for electrical machine, for example, to have a high energy efficiency and also that we can easily recycle. And finally, we have to make Europe as independent as possible related to the supply of raw materials. And so we have to avoid the use of critical raw materials that, like some we use heavy rare earth material that we use in permanent magnet. So to reach these objectives, in fact, the European Union launched a call related to high efficiency and low-cost electrical motors for circularity and low-use rare resources. So in fact, 5 projects were accepted. So you have Maxima, we are here today because of this, but also you have 5 other projects, so sister projects, EMTech, Climaflux, EFT, and Voltcar. So I encourage you also to look at this project, because we had a conference, so a RTR conference, so 3 weeks ago, so in Brussels, and they presented very, very interesting results. And if you are interested also in components in electric car, you can have a look also at the Evolve cluster in which Maxima belongs to. So about the context of Maxima project. So if you look at the electric motors you have in electrical car, mainly it's a radial flux machine, Why? Because you can get very good performances with such kind of a machine. The manufacturing is well known and it's low cost. If you look at, so you have AXIal flux machine also in automotive, but they are mainly dedicated to luxurious car and esports because they are very performant, but they are very expensive. So the idea is to say, okay, so we have a machine, an electrical machine that could be very performant, in fact. So it's a very good potential candidate to address automotive core market. So it's our goal, our target. But if we look at the performances we have, in fact, currently, the performances are below the EU specification. I will show you later what are the specifications. It is a costly solution, and you use critical raw materials, especially because you use permanent magnets. So the objective of Maxima is to design an axial flux machine, its manufacturing process, and its digital twin for automotive application with a limited environmental impact and limited use of critical raw materials. So I won't go in detail, but you have here presented, so on the left, so the KPI, so the key point indicator fixed by the call, okay? So you can see, for example, that they are very exigent in terms of, for example, of performance, in terms of torque, massive torque, for example. We have to go up to 10 Newton meters per kilo. Or in terms of manufacturing cost, we have to be lower than 6 euro per kilowatt, and so on. But it was not sufficient for us, not sufficiently challenging. So this is why we add over KPI, so it was our own KPI, and we wanted to reduce the energy consumption in order to have an efficient electrical machine. And also, we wanted to design an electrical machine dedicated to the automotive market. So it means that we added, so not me, but Stellantis, one of the partners of the project, provide us additional specification in order to design an electrical machine adapted for the automotive market. So if you look now at the partner of the project, so there are Stellantis, as I said, as a car manufacturer. You have E-Motors, which is a company dedicated to the design and the manufacturing of electrical machine. For automotive, you have OCAS, who is an electrical steel supplier, Oganas, who is a soft magnetic composite supplier, Mimplus, who is a permanent magnet manufacturer and also recycler, and for Multiphysics, who is an expert in the design of electrical machine. You have also Feuga, who is in charge of the communication, the dissemination, and the exploitation. And we have universities. So the University Polytechnic of Catalonia, who has an expertise in thermal modeling and also in management of digital twin and the control of electrical machine. UTCN, so the University of Technology of Cluj-Napoca, specialist in the design of electrical machine. VUB, so from Brussels and Belgium, specialized in life cycle analysis. And finally, Arts et Métiers and the University of Lille, specialized in the domain of EM manufacturing, life cycle management, and also digital twin. Just one thing to add is that if you look at the consortium, we cover almost all the chain value of the electrical machine. So this is something that is for us very interesting. So about the timeline, so in fact the project started 2 years ago. So in February 2023. So we started with the specification. So we defined the specification of our electrical machine. And then we started the design. So, and as well at the same time, so this is something important, that if you want to design an electrical machine at low cost, you need to design the electrical machine by itself, but also its manufacturing process. It means that you can design the best machine as possible. If you are not able to manufacture it, it is useless. So you have to do at the same time both. So this is what we are doing, in fact. And so we are almost now at the end of the process, and now we will start to manufacture the prototype. So in parallel with the design of the electrical machine, we are working also on the design of the digital twin. So the digital twin is, in fact, a digital replica of the electrical machine. So the idea is, once a machine is operating, okay, in parallel you have the digital twin, and the digital twin will enable you to have access to any information inside the electrical machine. You have also some work ongoing about the disassembling and the recycling of permanent magnet, because as in permanent magnet you have critical raw materials, as I said, so the idea is to recycle them. And finally, what is important is that we assess all our solutions, so using tools provided by the life cycle assessment, in order to evaluate the impact of our solution, so either the electrical machine by itself, but the manufacturing on the environment. Okay, so thank you very much. So if you have some questions or remark. So as it was said by Angela, so during the different presentation you will have in the following, so here in the attendance you can ask questions, so raise your hand, that's it. But online you have a chat, and so you can ask questions if you want, okay? So don't hesitate to do it. Okay, so we will switch to the next. So we will switch to the next presentation. So this will be done by Abderrahman Redbaoui and Claudiu Cătovanu. So Abderrahman from the company Motors and Claudiu from the... sorry? Sorry, I forgot Carles. So, and Carles also from UPC. So, the floor is yours.
Thank you. Hello everyone, hello online also. So for this part, we'll present the principle of design of an electric motor with axial flux for automotive applications. So by taking into account all the multi-physics point of view or challenges from electrotechnical, mechanical and thermal and other constraints also. So for the V-cycle, for the design of an electrical motor, we have a V-cycle from studies and to tests and validations, but now we must add some recycling to protect our product and to have a good a product with good environmental impact. You can name it. For our part here, we will talk only about the design and how we begin a design and what will be the result of only the electric machine parts. So for the first part, we will talk about electrotechnical. So in the beginning, we're beginning with a state-of-the-art and comparison of different type of electric motors, axial flux, and then we can include all thermal and mechanical constraints and do some loops to obtain the best structure. Yes, the best structure. This is the principle of the design of an electric motor. We can show this by this figure. So before the beginning of the design, we must see the car performances in terms of peak torque, max speed, gearbox, integration constraint in terms of volume and weight, and electric supply. So we're beginning generally with simplified analytical pre-design, electromagnetic and mechanical and thermal finite elements models and simulations to have a good electric motor, or best, if we can find the best electric motor, by taking into account the LCA and cost and the WLTP efficiency, so for the electric car parts. For the electromagnetic challenges, in our project, for example, we're beginning with a simplified analytical model to have the big, the main parameters. We confirmed this by finite element calculation, which in 2D, which take time, and with an optimization and parametric study in 3D simulation, which take time but give precise results. So, sorry. For the electric cars, generally we find two types of motors. We have radial flux motors. My colleague Stefan talked about these two motors because the flux in this magnetic flux in this motor is in radial direction, and we have axial flux motor. Generally, radial flux motor is conventional, so we find it with different form. Induction motor or wound rotor motor or permanent magnet motor with Tesla, Audi, BMW, Renault, and Toyota, and Stellantis also. So all manufacturers use radial flux motor in this moment, except some special car or sport cars. So for this radial or axial flux motor, the first choice to do is the materials. We must find the best materials in terms of magnetic core, winding, and permanent magnet. We have different material, but we can classify them in terms of performances, cost, and environmental impact. And also we have inactive parts like frame, fan or cooling systems, shaft, and insulation. This also we must be careful in terms of cost and environmental impact also. If we, for Maxima project, we concentrate on the axial flux motor, we can find different structure for the axial flux motor. We can find concentrated winding, distributed winding, sorry, for the stator, concentrated winding for the stator, surface-mounted permanent magnet, internal permanent magnet with different form, and we can find with double rotor, double stator, and we can go also to find different number of magnet poles and stator tooth combinations. So it's a very large choice, which is a very big challenge also to find the best structure to take into account, by taking into account the car and gearbox performances and the KPIs. And generally, not only for Maxima project, I think for all the projects, the designer try to find a compromise. For our case, it is WLTP losses, so it's losses in a drive cycle for the car compared to the continuous torque density, so big torque and low weight or mass, if you can. The Maxima KPI are here for our project, and we find some Pareto front to choose our best structure. We presented here also some relative impact of electric machine losses for different parts of the machine, have like a percentage which impact the losses. So we can act on this parameter to improve our structure. And finally, if I can explain rapidly, when we do electric machine design, so we have different factors. The important one are the number of the turns or conductors, magnetic circuit and permanent magnet, and geometric parameters. And in terms of performances, we have torque, speed, power, and some other constraints. So we can see that when we modify one parameter, we can improve performances, but we degrade other performances. So it's the compromise is not easy to find it, but all works. We have two works on Maxima, for example, to find the best structure where we can respond on all Maxima KPI, but also the Stellantis car manufacturer specifications also. And I finish with the electrotechnical part, and I let my colleague from UPC to continue with.
Thank you, Abdul. Then we shift to the thermal aspects, as he commented. I will start with just a general word about which is our requirement, which our overall challenge is that we need to increase the power density. This is general in all the electric and electronic fields, so apply to batteries, to power electronics, but here in particular to the electric motor and in particular for the automotive application and the AXIal machine. So in general, as we see in the picture, we are progressively in the field going to higher power densities, higher volume torque densities, and this is something that obviously creates a thermal challenge. Okay, we have higher power, and then we have higher losses, we have less volume, so we have a higher concentration of the dissipative heat that we need to extract from the machine to work at the correct operating temperatures. Okay. So summarizing which are the actions we can take to address this problem, the first point could be we can think on trying to reduce the losses. Here are two examples of how this can be done. The first is to try to segment the magnets to change the losses on their side, or to change for example, the conductor topology on the stator that could also address reduction of some part of the losses that we have on the coils. The second action we can take is to optimize the cooling design in different senses. The first one is that we can have different fluids, we can manage them together or particularizing them for different parts of the motor, rotor, stator, or power electronics, trying to, let's say, extract the best properties, the best temperatures to each particular target. Okay. Second, once we decide the fluid that will address each part of the problem, we can work in the design of the thermal, let's say, configuration itself to try to maximize the heat transfer coefficients and to try to extract the best from the temperature difference that are available in order to extract more heat. And the last one that typically is more difficult because it affects the rest of the vehicle is to try to adapt the vehicle interface to extend to other cooling options, to other temperatures that could be more beneficial, or to change the mass flow limits that we have for our motor. The final point that we could address is also to change the materials, because the temperatures, the limits we have, both on the magnets and on the coils, are dependent on the grades, on the materials, the quality, the composition, and so on. For example, for the magnets, we know that if we increase heavier rare earth composition, we can extend the temperature range. However, don't forget that in Maxima, the requirement is the opposite. We want to reduce the rare earths, so we have an additional constraint from the thermal side. We will know that our magnets will have lower threshold for their working temperature. And finally, we can also work on the conductors to let's say, include in the motor better grades that could withstand higher temperatures. If we go to the challenges, let's say, on the thermal perspective in more detail, just an overview. We have, as Abdu already commented, the dual stator and the dual rotor topologies, okay, which are the main issues on both. For the dual stator, as you have seen, we have the rotor in between. So this is where we have the most relevant problem. We have the rotor trapped between the two stators, okay? Then the problem is how to address the cooling of those magnets that are in that space. You need to take into account that the air gap between the stator and the rotor is of the order of millimeter, okay? So we have a very small space to cool down the rotor, okay? Then, in terms of when we think of different kind of fluids or technologies in terms of thermal management, we can first start thinking with using air, like getting air to extract the heat. But air is a bulky solution. We need, let's say, big ducts, so it's not appropriate for small units. And we have also taken into account the dirty problem. So if we ingress air from outside, we will probably face problems with dust and contamination. The next probable or possible thermal management action could be to use high thermal conductivity inserts that are different kinds, solid, biphasic. But here we have several limitations as well, because we need to take into account that these devices, these inserts, will be placed in the rotor where we have the magnets. So we need to take into account that these elements could not distort the electromagnetic field created by the magnets, and we take into account as well that their presence does not increase the losses, because if they are conductive, we have new losses that will create additional problems. Okay? What else we can do? We can work internally with fluids. In this case, we have problems regarding how to manage the centrifugal forces that we have in the rotor, how we manage the leaks. And if we want to cool it externally, as you have seen, the space is very limited, and we could have problems of clogging the air gap or increase the friction losses. To finalize my comments on the thermal side, if we go to the dual rotor topology, we are now seeing the opposite. We have the stator trapped between the two rotors. So now the problem is the opposite. The main problem is how to cool the stator. The comments about the technologies are similar than before. I will not repeat them. But let's say in this case we have three main issues. The first is how to address the cooling of the inner radius of the stator, because it's inside the internal donut, let's say. How to address this cooling of the internal side. The second is that the space between the tooths is very limited, and we need probably to address how to cool the tooths and how to flow something in this small space between the coils. And the third one is that the iron losses, so the tooth is, let's say, coiled by the conductor, and these losses inside are like trapped inside the coils. So it's again another challenge how to cool this tooth. Okay? This is everything from my side. Thank you.
Okay, good afternoon, everybody. In terms of mechanical constraints, I will tackle the rotor first. So as you saw, in terms of the dual stator topology, we already have thermal issues with the trapped rotor. So from a mechanical point of view, in order to avoid any additional losses in this rotor, we have to use non-magnetic, non-conductive materials such as plastic, PEEK, glass fiber, carbon fiber, combination of these. Well, the fact that they have low density, it's a positive aspect, but on the other hand, they have low structural integrity, so it means that we are going to have issues with the bending of the rotor and also the maintain of the magnets in the radial direction due to centrifugal loading. For the other topology, for the dual rotor topology, we had the main issue is the disc deflection. Why? Because at low speed, high torque, high axial forces, as you see in the first image, the rotor is bending towards the stator. However, at high speed and low torque, low axial forces, the rotor is bending in the opposite direction. So basically, from low speed to high speed, you have this movement of the rotor moving towards the stator and then in the other directions, causing fatigue loading into the rotor, and also which has to be assessed through transient phenomena. In terms of magnet, we have issues for the dual rotor topology because in this case we have surface-mounted permanent magnets. They are sensible to high speeds, centrifugal loading, and axial pulling. They tend to peel off the rotor and detach from the rotor. And also when they do that, they induce stresses inside the magnets, and as you can see in the top right picture. This effect is even worse when you have segmentation, and we need segmentation to lower the losses on the magnets, but in this case, the peeling off phenomenon is even more accentuated by having these small bits which are glued onto the rotor disc. If we move to the stator design challenges, for the dual stator topology, we identify three main designs possible. A fully rolled lamination stator, which possesses challenges due to the delamination of the yoke. A fully SMC stator, which possesses challenges because of the brittle behavior of the SMC, so it's not easy to fix into the flanges and housing. Or a hybrid solution, which is a compromise, which is a combination of roll lamination yoke with SMC teeth, which again, we have issues with assembly process tolerances which yield into structural instability of these such components. And for the dual rotor topology, now it's the stator which is trapped. Again, we do not need additional losses inside the stator, so we need to use non-magnetic, non-conductive materials to hold the stator inside the housing. As you saw, these materials have low stiffness, so we might have issues with the dynamic behavior of the stator, therefore the dynamic behavior of the entire machine. And finally, I will address the air gap control and the bearing design. These two are related. So the air gap control depends on electromagnetic forces, bearing choice, size, axial preloading, stiffness arrangement, tolerances, assembly process. We want to have symmetrical air gap values. So asymmetrical air gap values means dynamic unbalance, and for this, bearings play a critical role in maintaining equal air gap values. So in terms of bearing design, we have to assure this uniform air gap. Due to manufacturing, that's not going to be possible. So what happens is that you have an axial resultant on the bearings, which will cause additional loading, combined with the modification of the internal plates due to temperature. Basically, you will add internal pressure inside the bearings, increase the frictional moment, and damage the lubricant properties. So we need to address this proper management of the preload to reduce the noise level, enhance running accuracy, maintain precision of the air gaps. And it's something that is not very easy to do. So, and the last thing about the bearings is that they are more, their size is more determined by the critical speed, so rather than the force magnitudes. So in conclusion to everything that you saw in this presentation, these complicated challenges, they have to be addressed through a multidisciplinary approach, synchronizing electrotechnical, thermal, mechanical design loops, but in the same time with respect to materials, manufacturing processes, and of course cost. A close collaboration between the different teams, and of course use of suitable tools, analytical methodologies, multi-physics simulation tools, and of course testing facilities to validate all this numerical data. Okay, thank you.
So now we will switch to the next presentation. So the question and answer will be done at the end of this session. So I remind people online that they can ask a question on the chat. So now it's time to have a presentation about manufacturing process flow for axial flux machine, overcoming challenges for cost-effective mass production. It will be done by Johan Deak from eMotors.
troisième, oui.
Hello, everyone. So we'll continue a little bit what in the line of the previous presentations. I don't know. Yeah. As Stefan said, we are going to switch a little bit to the manufacturing, which is a good continuation of the structural issues that we saw. And here are the subject will be the overcoming challenges for cost-effective mass production. So the idea again is to look at how we can mass produce these motors. Here is a slide which may be intimidating at first, but I think the message that I want to show you here is that really the project, I think, was well designed from the beginning. Because what this shows is that different work packages are working together in parallel, and maybe the most this one, sorry. The most interesting loop on this slide is this one between the manufacturing process and the design. Of course, there are all other work packages that need to come into play in order to really work at the manufacturing. But I think this loop here is a very important cycle that we needed to address, and I think we did it up to this point in the project. So we will see some interesting results. Just to maybe go into more detail or to show an example of this loop, I took an example. So here is an example of a decision that, and we are going to see the impact on the design for a simple product or manufacturing decision. And the decision that we are going to explore in this slide is the preformed winding. So meaning you manufacture the winding separately and then assemble it on the tooth of the machine. Yes, so it is a very easy, very tempting solution because it's easier to automate and to production and to make the assembly. The assembly will look something like this at the end, and of course this already gives us some challenges for the tooth, because if we want to produce the winding like this, to preform one, then we need to insert it somehow on the tooth. Yes, and here we see already some options that are opening up about how to design the teeth of the stator. Now, these options here, of course, will add up some additional issues. For instance, if we go on with this teeth in two components, probably SMC will come at hand to use for this type of design. Of course, we can see that we'll need to use some adhesive or some glue in the middle to connect the two components. And of course, for the other solution, when we choose to do it a little bit differently with two tips like this, of course, we are going to see even more adhesive that needs to be added. This will have some consequences. For instance, for the electrotechnical impact, we see that we'll end up with a bigger effective air gap. On the mechanical impact, less stiffness, less resistance to axial forces, because again, in the tooth we do have high axial forces. Design impact, the additional axial fixation elements are needed, additional tolerance issues in the air gap tolerance chain. For the process, additional components, additional heating and curing time. The LCA impact, the curing requires additional heat consumption, so it's more energy that is consumed to produce this tooth. And of course, disassembly and recycling must be also considered to adapt the recycling and to this process. So it's just an example to understand the impact or this loop between the design and manufacturing. Yes, of course, I will mention in this presentation a few more issues. I will not go in this kind of details, but it was just an example to understand a little bit how this design and manufacturing must go hand in hand. So the first group of issues is grouped on this with this title, air gap control in manufacturing and operation. So the point will be that we'll need to control the air gap, yes, during manufacturing and during operation, yes, during the working of the motor. Now, this is a typical axial flux motor section. So we identify here the rotors. It's an example with two rotors, an example with a central stator, yes. And here are some initial points about this issue of the air gap. First, we do have two air gaps, yes, that can go up to as low as 0.8 or maybe even lower in terms of distance, yes. So this is a challenge compared to the radial motors where we are used to one air gap. Operating speed, I put here some reference speed of 12,000, but it can go up or even low. On the market, currently we don't see rotating speed as high as this, more to about 8,000 RPM with even higher RPM with some 1.5 millimeter air gap. So the mechanical limitations at maximum speed are one of the key constraints on motor performance, meaning that this rotor will turn, and the integrity of the rotor is a limiting issue. Again, it was mentioned multiple times, but we do have these axial forces that we need to take into account. If we look, for instance, at a stack-up tolerance study, very quick we end up with the result that we need very tight tolerances requirements on most components. Yes, so this is the obvious first result. If we use, for instance, typical components like SMC, a laminated stack, when we cut it, we end up with tolerances that can vary depending on how well we work these components. That can add to the tolerance study, and also if we add the bearing play, which can be also quite important, we see that this type of tolerances are quite high compared to the initial air gap that I mentioned. Now, here are some solutions that we worked on. Now, probably we won't need all of them. I just present the most of these solutions, and we'll go through the solutions a little bit, and we'll discuss their pros and cons to this as solutions for this issue. First will be to do some machining operations on sub-assemblies, for instance, on the entire rotor or stator. So to make this machining on different components. The process needs to be carefully assessed. Even if we discuss about SMC or laminations, because of the potential impact on performance. So in both cases, this needs to be done with very carefully. Also, if we do that on the magnets, this needs to be maybe the last resource that we want to do, because of the potential cost and safety concerns. Other surfaces that can be machined, if we look at the lamination surface machining, this again needs to be looked at because of the impact on performance. Another solution would be to enforce the air gap distance during assembly with some spacers. So we have these spacers that we can use. Other solution is to use shims to account for tolerance issues. Again, these are possible solutions, shims like this one, to position the rotor. Most of these are typically a bit time consuming, and it may be also more expensive for production. For the bearing, the solution will be to use a stiff bearing arrangement again, so to eliminate the bearing play with either 2 or 3 angular ball bearings. And also, again, to the bearings, use a precise and rigid preloading, which is more difficult to set up, and it might add to the cost and other issues. Another set of issues is on the non-magnetic and non-conductive materials in air gap proximity. Most of these issues we already discussed. The design stator flange may be needed for oil circuit sealing, structural integrity of the stator, for flooded impregnation, for axial fixation on the teeth. For the rotor, we might end up with some magnet holder or even a sleeve. And also, we shouldn't forget the axial forces that come into play here. And we also, close to the air gap, we cannot use steel, aluminum, or flanges, or steel or aluminum in the components that are part of the air gap. So, of course, the solution will be mostly concentrated on a design with plastic composites or overmolding to fix the components with glue or adhesive. Move on. So this will be a composite non-magnetic sleeve or magnet holder like this or here. This can be the solutions that can mitigate this, or PEEK or adhesive that we can use. And of course, again, if we talk about the adhesive to fix components, this will come into play. We must consider the segmentation, the laminations on the rotor, on the stator disc, and the SMC components to form the SMC blocks. Yes, all these components can be used with, or should be can be used with adhesive. Yes, so these are different solutions as I discussed, and hopefully with I need to close. I see signs that I need to close. Sorry for this. Another issue that I wanted to that I mentioned here is the balancing of the rotor. Again, is the same issues. It's a similar issue that need to be addressed in the manufacturing process. Thank you very much.
So thank you, Johan, for this very interesting and detailed presentation. So now we will go to the next presentation about ferromagnetic materials and manufacturing process. So optimizing axial flux machine for automotive applications. So this will be, the presentation will be done by Hamed Abdulazed from OCAS and Marcus Lindberg from Oganas. So Hamed, the floor is yours. So, Marcus is with us, so you will start with? You will start?
Yes.
Okay. Full screen. Okay.
So, good afternoon, everybody. Today I will try to give you an overview about the ferromagnetic material together with my colleague from Oganas. He will join us via online. So the title, as you see now, it's ferromagnetic material and the manufacturing process, optimizing axial flux machines for automotive applications. So my name is Ahmed Abulazid. I am research engineer at OCAS. So at the beginning, I would like to give you an overview, quick overview about the company and our business core, which is related to Maxima project. So OCAS is a research institute mainly for material science. So we are working mainly with steel. OCAS is a joint venture between the Flemish government and ArcelorMittal, with around 150 employees. 60% of them are researchers, with more than 20 years of experience in electrical steel characterization and modeling. OCAS is, as I said, from Belgium. We are located in Ghent, with the headquarters in Zilzata, where you see this nice building as a bridge from the industry and to university and to the application. And the second location is Zwijnaarde, which is location with Ghent University campus. From ArcelorMittal side, as you know, ArcelorMittal is the steel producer for not only for electric steel, of course, but for different types of steel. Related to electric steel, our ambition here to triple our current production. So right now we have the plant in Saint-Chili, which is a downstream plant, with upstream plant in Fos. In this year, we will produce from the north of France, from Dunkirk and Mardyk, in order to triple our production line and also to fit the automotive sector, of course. And as you probably know, now we also invest in new plant in US very soon. So related to Maxima project and related to electric steel, what we have from ArcelorMittal is a brand name iCare, which is electric steel for automotive traction applications. As you know, we have different requirements from when we design a motor, as our colleagues explained. So you need motor for high motor torque, high energy saving, and high power density. So each one is related, not only related to motor, but also it has an impact on the vehicle performance, like the high acceleration or compact and easy to go to high speed, or even smaller battery size. In order to reach this one, there is strong correlation between the ferromagnetic material and the motor performance. So high motor torque requires high magnetic polarization steel, and high energy saving requires high or low magnetic loss, and high power density requires high mechanical strength. Our electrical steel offer is organized over these three axes of function properties of electrical steel. So we have what's called I-care torque is optimized for the highest mechanical, highest magnetic polarization, which will produce at the end high mechanical torque. We have I-care save is optimized for the low or the lowest magnetic loss for the highest efficiency. And also we have I-care speed, which is optimized for high mechanical strength for high speed motor. On top of that, we have I-care 420 save. So 420 is the guaranteed yield strength at 420 megapascals. Save also, which means it's a combination between high mechanical strength and low loss. So as you see, this is a kind of different families from I-care, and which is optimized indeed for wide frequency operation and is available from 0.2 up to 0.35 for different characterization, different polarization, different frequency level. Related to manufacturing of such steel in radial or axial machine, as you know, probably you have different techniques. But for axial machine, it's a bit different. So we have different techniques like punching or slitting, rolling, and for each one we have to decide what is the impact on the magnetic performance and also mechanical properties. And on top of that, next to the cutting and shaping, you have also stacking, which is using, let's say, gluing or adhesive bonding. So in each step here, we need to study what is the applicability of our steel on the motor performance and what's the effect of such technique on the final product of the motor, which is our contribution in this project. This from my side, and now I invite my colleague Marcus to join, and the floor is yours, please.
Let's see if I can share from my screen here. Can you see it?
Yes.
Perfect.
No, not now. Not now, Marcus. Before, yes, but not now. Now we can see you.
Now we can see me. Okay.
Yes.
Let's see then. Try again.
Yes, that's okay. So now we can see both, you and the slides.
Perfect. Okay, so Marcus Lindberg here from Höganäs. I'm going to talk about soft magnetic materials. And Höganäs offers metal powders. We are the world leader in metal powders. Our SMC is soft magnetic composite, is called Somalloy. So we have different grades of this. And it's based on pure iron powder with an insulating layer on top of it. So in practice, what Höganäs is offering is this bag of powders, which we sell in tons.
Marcus, if you switch, we cannot see the slide is always the same. So
it's the same. Oh, sorry. Then we try again.
Yes. Okay. So now we see the. Okay.
The slide.
Yes.
Okay. So Höganäs is selling this bag of powder to our customers, who is then compacting this into components, which is later sold to OEMs and tiers to be placed in electrical motors or in electronics. Very fast, I think you've seen this before. This metal powder is compacted with very high pressure into high density components, which later goes through the furnace for curing. And typically 650 degrees. So we don't sinter these particles together because then we would destroy the magnetic properties But what we can in these two process steps is to optimize the process to reach a specific requirements or to fit the application needs. So it's a combination of these two process steps, which is a key to get the final performance. What we have done during this project, we have developed new materials, of course. That's always the goal for Höganäs, to come with better materials. This process has gone on for quite a long time, about 30 years soon. The latest version we have is what we call XSMC 26, which is our lowest loss material. And also we try to now push the mechanical strength of this material to increase what we call the 3P version of our materials. To come back a little bit to previous speakers, we have also looked at different design options when it comes to cost and the CO2 emissions for the SMC stators. And here we have the three examples as we've seen previous. The reference case is just having one part, and then we have the split in the middle, and then the third option is the hybrid combination with SMC tooth tips and then the lamination in the middle. We have used a software from Polarix Costings and their database to look into this. And now we're only looking at the SMC or the stator parts. So the reference case here we set to 100% or 1 in this case, and it's this topology with one component. If we start splitting it into two and use both with SMC, we see that the cost increases somewhat, and also the CO2 emissions. If we would have done one piece component in lamination, we see that the costs increases a little bit, but what is significantly increasing is the CO2 emissions from 100% to 300%. And the last three cases is these hybrid combinations, where we also see that the costs increase significant, and also the CO2 emissions, which could be one input to the project. And I would say this is one example where we have used some assumptions also. So it's a clear indication, I would say, in terms of cost of CO2. Another investigation we have done is also to see if we can machine this new material into the components we would like to use. And we see that we have quite good machinability with this. However, we still experience the same as we do with other materials. We have someone called Somaloy prototyping material, SPM, where we see like chipped corners and things like this, and that we also see on that material. Compared to if you compact the component, you will not get these chipped corners and edges. The magnetic properties with this new material is better compared to the prototyping material we have today, and also the mechanical strength is improved. And the last slide is some feedback to the project. To take the next steps from our side is that we need some more inputs to take the next steps we're close now to design freeze, but that is what we need to take the decision what we will do when we will compact or machine the parts. to make some prototypes. Also, from the start, we didn't really know how many motors we were aiming to build. It was a little bit higher than we first estimated. So that means that we need to produce a little bit more SMC prototype components than we thought. And then it will probably be cheaper, depending on which design we will choose, that we will actually buy a pressing tool to one of these presses rather than machine out components. Thank you.
So thank you, Marcus and Hamed, for this presentation. So now we will go to the last presentation. So about digital twin methodology, specifications and application for AXIal flux machine development. So it will be done by Daniel Montesinos from the University Polytechnic of Catalonia.
Okay, good afternoon, everybody. Thank you for being here. I am Daniel Montesinos. I am with CIUPC, Research Center in the Technical University of Catalonia, and I will explain you the methodology we are using to develop a digital twin to address the objective of the Maxima project. So one of the objectives of the Maxima project is to reduce the rare earth materials content in the motor. And the second objective is to increase the efficiency or reduce the energy consumption of these motors. This energy reduction can be done in two ways. The first one can be the design of the motor. Of course, these are the topics we have been addressing until now, the design of the motor. But we can also reduce the energy consumption when the motor is operating. So by control, by the control algorithm used in the control system during the operation of the motor. And this is the objective of the digital twin, to obtain data from the real-time operation of the motor that can improve the control system, thus reducing the energy consumption in the operation. Also, with this digital twin and the control system, we can get other advantages, not only energy reduction, but also, for example, increase the performance of the motor by getting more torque with the same amount of current, for example. Also, we can use the digital twin for other aspects, like, for example, thermal derating, so monitoring in real time the motor and avoiding overheating and damaging the motor in these stressed conditions. Also, the digital twin can be used, for example, to refine control strategies. In fact, to develop our optimal control strategies in this project, we are using some of the, let's say, outputs of the models implemented in the simulation of the design of the motor to be included in our control strategies. So all these aspects, and even probably more, can be developed using the digital twin. The methodology we are using will be explained now, and this is the general scheme of the digital twin. So we have some inputs coming from some measurements, the current, for example, the rotor position, temperature of the cooling system, some inputs about the control of the vehicle in terms of the duty cycle and the requirements of the driver. And with the digital twin, we will obtain these 4 vectors. The first one related to electric parts of the motor, inductances, resistances, EMFs. Then related to the losses of the motor, related to the temperature of the motor, and also related to the bearings lifetime. So to do that, we have divided the digital twin in three parts. The first one is the electromagnetic part, the second one is the thermal part, and the last one is the bearings and the mechanical part. The electromagnetic digital twin, the objective of this electromagnetic digital twin is to obtain these electric-related variables, like, for example, the torque estimation, inductances, resistances, and back EMF related to the electrical elements, but also the losses in the windings, in the iron, in the magnets, to be the input for the thermal model that we'll see later. Also to estimate the forces present in the motor to estimate the bearing lifetime remaining time. The methodology for the electromagnetic digital twin is based on first developing a high fidelity model using finite element method, and then using a model order reduction to obtain a simplified version of this high fidelity model to be implemented in a device and to be able to be running in real time. For the thermal digital twin, the approach, of course, is similar. We need the losses computed with electromagnetic digital twin, the motor speed, and also the temperature of the cooling systems, the temperature conditions of the cooling systems, and the output of the digital twin will be a vector of temperature of the most critical selected locations that can influence on the motor temperature and the thermal behavior of the motor. The methodology is a bit different than the previous case, and in that case we'll use machine learning techniques to develop a model of the motor. Using CFD cases at motor level or at parts of the motor level, we will train a model that later will be implemented in the same device to be implemented in real time. Okay. For the mechanical digital twin, of course, the approach will be similar. We have some inputs, some mainly due to mechanical variables, the motor speed, torque, and forces that are acting in the motor, temperatures also of the shaft, the duty cycle of the vehicle use, and the output of this digital twin will be the bearing lifetime and the bearing losses that will also be used as an input on the thermal digital twin. As you can see, all the digital twins are dependent on each other and exchange information between them. In that case, the digital twin will be based on analytical equations, based on reliability functions of the bearings, and of course will have to be implemented in the same device and also run in real time. This is the general view of all the interaction between elements. We have the power semiconductors and the motor. These are the physical elements that needs the motor to be controlled. And then we have the inner control that is able it's the responsible of control, the field-oriented control is the responsible to apply the voltages to the motor needed to make the current circulating inside the motor to generate the appropriate torque. Okay? And this field-oriented control will have some inputs from the digital twins. Adapting these control laws, we can obtain a better efficiency or we can increase the performance of the motor. In this particular case, digital twin will be mainly used into steps of the field-oriented control algorithms that you can see here in these white and black boxes. So the first one is to improve the current to be applied to the motor to obtain the desired amount of torque. In this sense, one of the main objectives is to reduce the current applied to the motor, to increase the efficiency in that way, but obtaining exactly the same performance or even better if it's possible with less amount of current. To do that, we need the variation of the parameters of the motors in real time to adapt the control laws in this case. On the thermal point of view, we can use the temperature estimation of the motor, depending on the duty cycle, to modify the maximum current capability of the motor, not to overheat the motor in these cases. So preventing the damage of the motor. As a conclusion, the objective of these digital twins, it's clear. The first one is to reduce the energy consumption of the system itself, not only the motor but also the converter operation. Okay, optimizing the control algorithms in this system, and enhance predictive capabilities of the degradation of the bearings and degradation of other materials. And this is the starting point of using these real-time digital twins for the operation of the motor. Thank you for your attention.
Thank you, Daniel. So we are a little bit late, but we will have time for some few questions.
So, are there any questions in the room? Please raise your hand and I will pass you the mic.
So I will limit my question, so okay, because I know we are late. So first of all, thanks for all the speakers. The representatives are very impressive and very interesting. So I have a very simple question. In fact, if I have well understood, it is for Abdou and for Johan. In fact, one of the problems is the forces in the pieces of the stator, because with the stockless, of course, stator, you have forces in the tooth, in the independent tooth of the stator. Do you think it is possible to choose, for example, winding topology which improve this fact, this point? For example, here I think do you have a lot of winding topology possibilities, and what is the criteria of choice you have used to, and in particular, do you have is the criteria of choice to integrate this point or not?
Thank you for your question. So, in terms of, I will talk about combination, choice of combination. We do
slot pole combination.
Yes, exactly, slot pole combination. So we do the several studies between I think 10 structures to compare different pole combination. 10 combinations, slot pole combination for the surface mounted concentric winding structures. And we find that by increasing the number of poles, we can increase the density because we use a very small yoke, but we increase the losses, which is not compact with the Maxima KPI. In the other side, with very low number of poles, we reduce the losses for the same speeds, but we increase the weight because we need a very high, very weak yoke for the flux, for the magnetic flux. So we degrade the density. So we find the structure 18 slots and 12 poles, so 6 pole pairs, which gives a good compromise between density and losses. Okay. For our case, for the speed and the specifications announced by Stellantis for the torque speed, because I think if the speed are very higher, I think we need to reduce the number of poles because in terms of yes, there is other structure which can give in terms of winding factor highest than 1812, but they present high harmonics, so we can't find.
But my question was more, was more, you know, when you choose the slot pole combinations, so of course you have a limited number of poles, so the number of combination is lower, but it acts directly on, classically, for example, in a radial machine, in cogging torque and in radial forces. So for me, the forces which are in the stator tooth are of the same nature. Okay, so perhaps there is something to investigate, to try to find perhaps a combination which acts less on the tooth. But perhaps with the compromise with other things, it is not so obvious, in fact.
So the discussion is very interesting. So we'll have a short coffee break after so you can continue the discussion. So we will switch to the next question.
I think I'm going to give the floor to the online questions because we have our audience there, and there are 2 questions on the chat. So, David Goose is asking if the oil cooling of the engine already set, or would be solid cooling still be an option? I think, Carles, you can answer this.
I would say we are not using only one action in terms of cooling. We are combining different actions, and in fact, they are still under optimization. We are not only the fact that we are trying to reduce losses, we are trying to change the balance of the losses between stator and rotor, and this, let's say, is oriented to achieve the final selection of the cooling. But let's say, in principle, we are not stuck to only one option, but combining them.
Okay, thank you very much for this answer. And then they have another question for the team in charge of the design. They want to know if you have considered the slothless toroidal stator core with 2 outer permanent magnet rotors, and if yes, if you have considered that option too. They want to know what's the reason for not having chosen this topology.
Abdou?
I will repeat the question to Abdou. They want to know if you have considered the slothless toroidal stator core with 2 permanent magnet rotors, and if you have considered this solution, why didn't you choose this one?
When you talk about slotless, I think the stator without tooth, I think. We can't use this type of stator, if we can name this, if we can name it like this, because we need a big peak torque for the car. So with these structures, we can't achieve very high torque values. So because of this.
Okay, so as we are late, if you all agree, the questions of the people in the room can be made during the coffee break, and then we will be back in 10 minutes. For the online audience, we will be back in 10 minutes. So see you in a while. Thank you.
Je suis désolé. C'est la bonne présentation. Ouais.
On fait comme ça, moi je peux la jouer à la mettre.
Ah ok, c'est... Okay, so now we start the new session. So about sustainability in focus, permanent magnets recycling challenges, and life cycle assessment for electric motors. So the next presentation will be about recycling challenges, managing end of life magnets, and it will be done by Maximilian Roof from MIM Plus Technology. Maximilian?
Thanks for the introduction, and also welcome from my side, also to the people participating online. As Stefan already said, I'm Maximilian Ruf. I'm a research and development engineer from MIM Plus Technologies. It's a company located in Germany, near the area of Stuttgart. I today want to introduce you to the recycling of permanent magnets and also the challenges that may arise during the process. Here's how I divided my presentation into 4 chapters. At first, I want to give you an introduction about the applications and the resources, so you will get a feeling for the motivation behind the recycling of permanent magnets. In the second chapter, I will introduce you to the metal injection molding process, because for us it plays a huge role during the recycling process chain. In the third chapter, I will come to the core topic, the recycling of the neodymium iron-bound magnets, and in the last chapter I will tell you some challenges during the recycling process. Here you can see neodymium iron-bound magnets and their application field. They are today by market value and also by market value and volume the strongest permanent magnet material. They were developed in the 1980s and then captured the market, which you can see in the graph on the right. Displayed there is the energy product, being an indicator to the magnetic performance of a material, and you can clearly see that the neodymium iron-bound magnets have the highest energy product. And this is why they are today used in a huge variety of high-performance applications, including e-mobility, wind turbines, and also drones. And therefore, the demand for that material is still increasing. The problem about the resources is that the reserves are not distributed equally worldwide, but there are some hotspots, which you can see in the graph on the right. You can see that China, in blue, has a huge share of the rare earth element reserves, about 37%, and Europe has only a much smaller reserve share, which is why you cannot really see a European country in that statistic. So the problem is that in the rare earth element production, the situation is even a bit worse. China has there a near monopoly position, and to show you that, I divided my, let's say, my observation into two groups. So first we have the light rare earth elements, which include neodymium and praseodymium. These are the elements that are absolutely necessary to produce rare earth permanent magnets, and also the heavy rare earth elements, including dysprosium and terbium, which are mainly necessary to improve the magnetic performance of the material. And you can see for the production of the light rare earth elements, China has a share of around 70% worldwide, and for the heavy rare earth elements, China has even 88% of the production share. So, and also the production of the rare earth elements is connected to some environmental aspects. First, you need to know that the rare earth elements are very difficult to substitute for high performance magnetic materials. And the mining of these resources is quite energy consuming and also costly. And the resources are mined under difficult or problematic conditions for the workers and for the environment, which leads to a major environmental damage. So you can see now a motivation for recycling maybe. Here you can see a map which identifies some materials with a high supply risk. And I mainly want to focus on the red areas. You can see there that both the light rare earth elements and the heavy rare earth elements are identified as materials with a very high supply risk. But still, nonetheless, they are used in quite a broad variety of applications, including wind turbines, traction motors, or photovoltaic cells, for example, which is why they play a huge role in the sectors of renewable energies and e-mobility. Here you can see a problem arising from the near monopoly position of China's reserves. Here in the graph on the left bottom, you can see the price evolution over time for neodymium in in orange, and for dysprosium, so a heavy rare earth element, in blue. And you can see clearly a strong spike in the evolution around the years 2011, 2012, which was imposed by or caused by export restrictions coming from China. So you can now imagine that there is quite a dependency situation resulting for Europe, which might be a bigger problem. But it's not hopeless. We have some measures to reduce the dependency on China's exports. We may produce the permanent magnets within Europe. That's the first measure. The second measure would be a closed material loop, so we are not so much dependent anymore on the raw materials or the virgin materials. And also a good thing is that magnet recycling has a very great potential. You can see in the European Union around 3,000 tons per year, and worldwide around 20,000 tons per year. So this could be a huge business. As I introduced, I want to also show you a bit the metal injection molding process, because this plays a huge role for our recycling process at Mimblos. You can see here that the metal injection molding process for neodymium iron boron magnets can be divided into 7 steps. And in the initial state, we can use virgin material, so-called strip cast flakes, which you can see on the bottom, or extracted end-of-life magnets, which you can use from old electrical machines, for example. For recycling, then the magnets need to be shredded first, so you get coarse pieces. In the next step, we will carry out hydrogen decrypitation, so we will use hydrogen to produce smaller magnet pieces, and afterwards a jet milling step, which produces the magnet powder for our production. In the next step, it's called the feedstock production. We will mix the magnet powder with a polymeric binder to achieve some flowable mass, which we will use in the injection molding process to reduce our green parts. The green parts already have the geometry of the final sintered part, but are still a bit bigger because they still contain the polymeric binders, which we need to remove in our debinding step. And afterwards, in the sintering step, the magnets will get fully dense, so we get a fully metallic material. And we can cover the whole process chain at MIMPLAS in-house. Here you can see some advantages of the process. First, let me introduce you to two competing processes. First, the present sintered magnets. They have the disadvantage that they can be produced only in quite simple geometries, but they develop a quite high magnetic performance, noted by the energy product. The second technology is the polymer bonded magnets. They can be produced in complex geometries, but the magnetic performance is lower. And our metal injection molding magnets try to combine both advantages, so we can achieve a very high shape complexity and also high-end properties of our magnet material. Also, we can implement complex magnetization fields, and another advantage is that we nearly need no post-processing, which saves us resources from the critical raw materials. And just a footnote, MIMPLAS is, to our knowledge, still the only capable supplier for metal injection molding magnets at an industrial scale to this day. Here you can see some examples for our magnets. We can produce very tiny parts with thicknesses down to 0.4 millimeters. We can achieve a very high shape complexity. You can imagine, for example, inner features like cooling channels or like fixation features on the bottom. We can also achieve complex magnetization fields, and we are also quite experienced in the area of electric drives. Here you can see, for example, an example for a radial flux motor as a cooperation project with a German company, Simo. Okay, so let me summarize for the moment. You can see now metal injection molding is quite a unique process for the manufacturing of neodymium iron boron magnets. Let me come to the main part, the recycling process of the magnets. Here you can see an overview over different process routes. We are always starting with used end-of-life magnets, and depending on their condition, you can either simply reuse them if they are still in a very good condition, or you can decide on short loop or long loop recycling. The difference is that short loop recycling mainly aims for the recovery of the magnet material, and long loop recycling aims for the recovery of the rare earth elements. In my presentation, I will only focus on the marked red process, the so-called hydrogen decrepitation process, which is the only recycling route we are using at MIMPLAS. Here you can see our closed loop recycling process. So as I already mentioned, we can use virgin material, strip cast flakes, or end-of-life magnets. We will transform them into a magnet powder. During our MIM process, we will produce complex shape, possibly metal injection molding magnets. There might be the necessity to add some additives to compensate losses during recycling, for example, rare earth elements or organics. After their use, the magnets are end-of-life magnets again, which we can transform then again into a magnet powder. You can see this is a closed loop process. We have the complete technical capability to do the recycling process, and we are also quite constantly involved in public funded research. Here you can see another core process in the recycling of the magnet materials, the so-called HPMS process. This is a short form for hydrogen processing of magnet scrap. I will now shortly introduce you how this works. our initial point may be some end-of-life magnets, in this example extracted from a hard drive disk. Then they will be put under hydrogen atmosphere. Let me first explain to you and then show you the video on the top. The hydrogen mainly attacks the neodymium-rich grain boundary faces of the magnet, here marked in red, and there causes some volume expansion, which will break the magnet material in its grains. And I can show you that process here. Let me note that this video is time-lapsed, so depending on the magnet size, this normally takes from hours to days, so it's quite accelerated. And after the process, we have two resulting materials. Now I maximized it. Two remaining materials: the neodymium iron boron powder, which we desire, and also some scrap materials, for example, coatings or adhesives, which we need to extract. But this can easily be done, for example, by sieving the material. And another advantage is that the powder can then directly be reused, utilizing our metal injection molding process. But also, let me note that this is a patented process from the University of Birmingham in the UK, which has to be addressed. Now let me come to the challenges in magnet recycling. I will highlight three specific challenges and then come to my conclusion. The first thing I want to highlight is the reactivity of the neodymium iron boron material, especially in its powder form. You can here see in the picture that this material is highly pyrophoric, meaning that under oxygen atmosphere it ignites spontaneously, which you can see here in the glowing parts. This is also, of course, a safety issue you need to address. You need to handle the reactivity of the powder during the whole process, especially from the contaminations of oxygen, nitrogen, and carbon. Let me remind you that metal injection molding is a binder-based technology. This is why I especially mentioned the carbon, because the binders mainly consist of carbon. And also you need to address that the alloys often contain elements like cobalt, which may be hazardous. So there needs to be you need to have some special equipment and process know-how to handle that reactivity of the material. The contaminations can also have a different effect. They can be degradative to the magnet properties. I want on this slide to highlight especially the influence of carbon and oxygen. Maybe let me start with the oxygen contamination. You can clearly see with increasing oxygen contamination, both of the important magnetic properties, the remanence and the coercivity decrease. And the effect on the coercivity is higher than for the remanence. Also, on the lower graph, which was developed by us ourselves at MIM+, you can see a similar effect for the carbon content. So with increasing carbon content, you will get a strong decrease in the coercivity, but a slight decrease in the remanence. But this is, of course, an issue because we want to aim for high-performance magnets. Here's the basic mechanism behind that degradation. Let me try to quickly introduce you to the topic. So in the beginning, I mentioned the heavy rare earth elements, meaning dysprosium or terbium. Here in this example, you can see the effect of dysprosium. This is desired only in specific regions of the magnet material, only in the shells around the hard magnetic grains, here in orange. So during the recycling process, you might get a loss of that heavy rare earth elements. The critical steps here are the jet milling, during which step there can be an abrasive loss of the heavy rare earths, and the sintering step, in which there can be a diffusion process. So the heavy rare earth elements diffuse into regions you don't want them to. and they are only effective if they stay in the grain boundary phase. So the effect is a property degradation, but there's also a solution. The solution is called grain boundary diffusion treatment, in short form GBD. So you can apply new dysprosium or terbium on the magnet surface, and after a heat treatment on the recycled permanent magnets, you will get a property increase again, which you can see in the graph here. You can see here in purple the initial state of the permanent magnet material, and in green the state after dysprosium GBD and of terbium GBD, which is even a bit better, but terbium is also a lot more expensive. And the goal is, of course, like you can imagine, restoration of the magnet properties, but also we want to use only a minimal amount of the heavy rare earth elements, because in the beginning I mentioned these are considered critical raw materials. And also here to mention, this process is also covered by a lot of patents. Okay, let me come to my, I think, last slide. I want to summarize here the challenges during magnet recycling. So you can imagine it's always better to extract the magnets from larger assemblies, for example, from wind turbines. Let me mention here that for some wind turbines, they will use tons of permanent magnets. This is, of course, better than using them from small electrical machines. There needs to be done a demagnetization step before the magnet extraction, especially if you extract huge magnets. This is just because out of a safety or a handling reason. You can do that by a thermal treatment or by a reverse magnetic field. Mixtures of magnetic materials are not desired because they will lead to contamination of the material. Also, during the use of the magnets, there might have happened some corrosion or oxidation. In the example on the right, you can see magnets that were exposed to seawater with huge, thick corrosion layers. You have to separate foreign materials, for example, adhesives or coatings, from the use phase. You have to minimize the carbon and oxygen contamination, because also they will decrease the magnetic performance. The property degradation during recycling can be partially compensated by the grain boundary diffusion, utilizing the heavy rare earth elements, dysprosium and terbium. And also, not to forget, there is quite a challenging pattern situation both for the grain boundary diffusion process and for the HPMS process. So let me come to my conclusion. During the Maxima project, we try to combine the potentials of the metal injection molding process with the short loop magnet recycling to restore very good high-end neodymium iron-bound magnets. Thank you.
So thank you, Maximilian. So now we'll switch to the next presentation about life cycle assessment. So the presentation will be done by Léa Damor from the VUB. I'm not able to speak in Flemish, so sorry.
Thank you. So I will discuss the life cycle assessments for electrical machine and how it was applied in Maxima to support eco-design. So first, what is LCA? I will present it from the perspective of Maxima. So the life cycle assessment is a framework that follows the standard from ISO, and it considers the entire life cycle of a product or a service. So you will look at the impacts from the raw material extraction to the final disposal of your product. So first, the goal and scope definition. So regarding the electrical motors in Maxima, so we are looking as I said, from the raw material extraction to the end-of-life management, with the specificity in Maxima of the recycling of the permanent magnet and an easier disassembled machine. What is important with LCA is that we can avoid a shift of potential environmental burdens. So to give small examples, you might decide to reduce the amount of permanent magnets in your machine for criticality reasons, for example, which will lower the impact from the production, but it might end up with a machine that has less efficiency, which means that the impacts from the use phase will increase. So you will have a shift here in your burden, and you need to find some kind of balance, and that's what you can see with LCA. Related to the inventory analysis, so we compile a lot of data that we get from the resources, pollutants, emissions, products, the waste. How do we get it? So from industrial partners, we gather some data and measurements. We have also existing database that provide us the LCA data that we need. We can get it also from the literature, and it's a continuum iterative process, which means that at the beginning of the project, of course, the data will have quite high uncertainty because we are not sure of what we are developing, and then the more you go to the end of the project, the more you have data, the more you have more qualitative data. Now regarding impact assessments. So in Maxima, we are focusing mostly on climate change and on the mineral resources indicators. I will focus mostly on mineral resources here first as a methodology. Climate change is quite common and well known. But here I will explain a bit more the mineral resource indicators and the challenge that we can have in LCA and from the perspective of the Maxima project. So quickly here we have the list of the European critical and strategic materials that have also been presented already, with the materials that you can find in the electrical machine. So so in LCA we have different ways of looking at mineral resources and different methods to calculate the impacts of using a certain resource. So what you have is first you have your resource, which is the amount of materials that you have in the earth crust that you will try to extract. You will have some extraction of exergy that you can quantify. And you can look also at the depletion of natural stocks. With the depletion, what we mean is the scarcity by using your resource and how it reduces the amount that you have in the earth crust. By mining it, you can have some degradation of the ore grade or also additional energy and costs that can come together with the exploitation of the resource. Then these resources are going to reserves and become raw material stocks. And then we can look with these stocks as also different method. One that will look rather at the supply risk and the geopolitical and market factors that can impact the materials. And what we call the dissipation. So the dissipation is when materials reach its end of life and cannot be used anymore. It means that you look at it from a perspective of end of life, where some materials can be recycled and reused, and you look at the time it reached its very final end of life and is not possible to be used anymore. So quickly, I'm just going to show here on that. I won't go into details of the method, but just to show a bit how it works for LCA and how we quantify it. So what we have is what we call characterization factor, where all materials are quantified depending on the different objective of your method. Here I have the example of copper and cobalt. So if you look, for example, at the depletion here, at the depletion of natural stocks, so which means that you look at the resources that you have in the earth crust and the extraction rate. You have the copper that has a higher characterization factor than the cobalt, and you can then compare the two thanks to this quantification. If you look at, for example, dissipation, copper is well recycled, so we'll have a lower characterization factor. So now regarding this method, they will have different goals and show different things. So for the depletion of natural stock, it will rather look at how the use of the certain materials will contribute to the scarcity of this resource. I have put also here the main metals that are in the electrical machine and characterized in the methodology. For the supply risk, it will look at how its use will affect and increase the issues and related to the short-term geopolitical and socio-economic aspects. And for the dissipation, then you will look more at the physio-economic resource scarcity, meaning after, while using it. What I want to emphasize also on that is that, so for the abiotic depletion method, it is the one that is in the environmental footprint methodology, which is the methodology that is developed by the European Commission and advised by the European Commission. However, in this method, the rare earths are not characterized, which means that we can't really see from this perspective their impacts. So here it's an example of the results that we have looking at the different mineral resource method on the reference vehicle. This is mostly to show that you can yield very different results and see where are the burdens on very different way depending on the method that you choose. This one being the one from the European Commission with copper, where it's the main burden. Another thing to add here is that I have added from a paper that have characterized rare earth for the depletion method. I have added the characterization factor, and what we see is that actually there are not a major difference by adding the rare earth in the methodology. Reason is that it's a methodology that looks at the resources where the rare earths are. There are a lot of rare earths in the earth crust. The problem will be more how to extract them, and then also at the end of life, how to recycle them. So in Maxima, we have decided to focus on two specific methods. The one from the European Commission, the environmental footprint related to depletion, so related rather to mining aspects and mining activities, but also to dissipation, which gives characterization for the rare earth in Maxima, and look also at from a perspective of the end of life of the materials. So to have a first conclusion just on the resource, so it is necessary in Maxima to assess this impact. It has been decided mostly because of the use of rare earth in permanent magnets. And you also have some strategic materials such as copper. You have very different type of assessments in mineral resource indicators. There are no right or wrong answers to what to choose. It really depends on the scope of your study and the goal of your study and what type of question you want to answer. For that, as LCA practitioner, we also have a decision tree that we can check that has been made by the organization GLAM. And so in Maxima, we will focus on the depletion and dissipation method, and the results will be shown for these two indicators. So now focusing on the recommendations from the LCA part for the electrical motor in Maxima. So how did it work for the steps? So we first look at the reference vehicle and did a literature review also on LCA of electrical machine to have first insights of what are the main burden for electrical machine. Then we have different versions of architecture and designs to which we have calculated a part of the LCA based on production and use phase. And the LCA was also included as a criteria for the choice based on the different table that you saw in the presentation that were before. Then we also compare the designs with the reference vehicle. We are now developing also a tool that is easy to use for the future assessments to show in an easy way LCA. And then the final step will be the LCA on the final prototypes. So regarding what our findings from the reference machine, so what we saw first is that when you look at with the European mix, electricity mix, you see that the use phase impacts are higher than the production impacts. You also have the production from only if you look only at the production part, you have electrical steel and aluminum that are the main contributors because they are very energy intensive process. And you see also great benefit from recycling to lower the impacts from the production as you avoid the production of certain materials. Then regarding mineral resource depletion, so here the dominant contributor is the motor production, and with, for this specific method, the production of copper. And of course, the recycling of copper, it is expected that it be beneficial to avoid its production. Now regarding the results on the different designs, so what we are showing here, so we have been assessing several designs to which a certain materials would change, and we got the bill of materials of this design and also their losses. So here what you see is a radar graph with the three indicators. The one at 100% is the reference machine, and then you see the different version. One thing to mention is that regarding the first 3.1 version, what we saw is that actually the impacts are higher than a reference vehicle, reference machine, which is related to higher use of copper. Then what I want also to highlight is that sometimes a version that will be better for certain indicators can be worse for another, which was the case here between version 3.13 and 3.12. 3.13 was the best one regarding climate change, but one of the worst regarding depletion, also due to the use of copper. Focusing more on climate change, so here on production and use phase. So what we saw from the mineral resource indicators is that basically the ranking in between the version was the same regarding production and even adding the use phase, which is not the case for climate change and illustrate a bit the trade-off I mentioned at the beginning. So here, what you see is that while you have a decrease starting version 3.11 in terms of production on climate change impacts, regarding use phase, since you have more losses for the different next version, then you have more energy consumption, and so when you add the two, they have slightly higher climate change impacts. Another thing that we have looked at with LCA is the sensitivity analysis around the electricity mix that we are using. You are taking the current European mix. Of course, if the machine is to be sell in the next decades, the electricity mix will change and hopefully be decarbonized. So we have compared an electricity mix from Poland, which are the results on the high bar, Poland with a high carbon-intensive electricity mix, and a quite decarbonized electricity mix from Sweden. And what we are observing is also then the production phase and part in LCA, in the LCA of the machine is becoming the most important contributor. Now regarding the comparison with just quickly with the chosen design to see more here. So we are already from production and use phase, we have already the chosen design that is performing better than the reference vehicle. But we will add also end of life to see also how it evolves. Now the last update that we have made in the latest weeks is that we have developed an LCA tool that you can find here using the website or the QR code. This tool is should be easy to use and easy to show the results of LCA. And the idea is that it can be used by everyone to see how certain criteria can impact your results. I can't show it here, so I will have it here. So the first thing is that you will be asked to enter different criteria. I have modeled this tool based on the criteria that were important at the time that we had the different designs. So for example, the mass of PM was changing. That's why I put here a possibility to change the mass of permanent magnet. And you have default value that are there. You can also choose the lifetime, but also the electricity mix, as I mentioned, between Europe, Poland, and Sweden. And you have also you can add also different parameters regarding the losses or the rolling coefficient, which is now set to the standard one for a car with a tire on rolling on the asphalt. Then what does it show? So you have, I can't show it here, but you have the results for the 3 indicators more specifically, and you have again this radar graph that you can see directly from a first version that you have made, and then you can add different versions. Here I just reduce for visual purpose, I just reduce the losses, and so that you can see the reduction here for climate change. And you can do that several times and download the results. We hope that we will see in the coming months, but we hope also that these tools will help support the eco-design of the machine. It's also quite flexible and can be adapted and changed to meet the new criteria that can be important and can change throughout the project. So conclusions from the life cycle assessments. So for the main learnings, so with LCA we can support the eco-design decisions in Maxima. We have been able also to provide some insights on how impacts may evolve over time, especially related to the electricity mix. And it also thrives on strong collaboration with partners. We have been able to get some LCA results also because we have been able to collect a lot of data from the partners already from the beginning of the project, even though these are preliminary data. So the results show that the chosen design is outperforming the reference vehicle now on all indicators, but also that the production phase remains crucial when we look at low carbon electricity mix. Just as information from a broader perspective, here we are looking at what we call attributional LCA, which is looking at a product, the input, the output, and how it affects certain components are affected by that. You can also have consequential LCA, and here you will look at how a change in the transport sector will affect the impact of your product or certain part of your product. For example, how the electrification of the fleet could impact the the electrical machine. And the next step for the LCA will be the refining of the LCA data once we have more data, the inclusion of end of life, and the final LCA also on the prototypes when it's done. Thank you.
So we have a short time for questions, if you have the attendance. No questions?
No questions in the room?
Thank you. I have a question about the LCA. And we talked about raw materials, so we talked about copper and aluminum and others, but I think we didn't talk about glue. I don't know if it's raw material or it's because I think it's a constraint to use some glue or resin. So
the challenge with the glue will come with the end of life, because what will be important in the LCA is to know the recyclability rate and how much you can take out of the magnet to reuse it in your machine. And this will depend on the type. If you use glue, you will have a lower recyclability rate, and then of course you will be able to use less materials. So that's where it appears in the LCA.
So we don't have any online questions in this part, so I think we can continue to the third part of our midterm conference.
Okay. So now we will, so thank you very much for the two speakers of the session. It was really interesting to have such kind of presentation about recycling, PM, and LCA analysis. So the next session will be about electrical motors, specification and requirements across automotive, aerospace, and marine sectors. So the first presentation will be done by Gilles Marquez from e-motors, who will be online. So, and it will be about the automotive sector. So, Gilles, do you hear us?
Yes.
Good.
Hello, everybody.
Okay, so you are. We can see you, Gilles. Okay. So you can share your screen and.
Okay, thanks. So I can start. So in this chart, what you can see is that the perimeter of e-motors. Just to remind you, e-motors is a company that is that has only 6 years old. We are a joint venture between ex-PSA. So
Gilles, we cannot see your slides.
Screen?
Yes.
Is it working now?
Yes, now it's okay.
Okay. So just to remind you, e-motors, we are a company, a joint venture between Nidec, Leroy Sommer, and Stellantis. We have only 6 years old. So we start in 20.
We can see you again, Gilles. Okay, now we can see both. That's good news.
Okay. I touch nothing now. In this chart, you can see all the products that we are developing. So we can start from only active parts, rotor stator. We have some applications with that, rotor stator on inverters, like for EDCT applications. We have also products with a complete motor without the inverter. The inverter and standalone. We have also developing our own inverters, making in-house. What we call the 2-in-1, motor plus inverter. And now we are already, after 6 years, we have also some applications with a 3-in-1 system. So we can see that we can cover all the perimeters that we can find in a 3-in-1 system. So that we can afford full BEV vehicles, but also hybrid vehicles. On this chart, we can see the strategy that we put in place since the beginning of the GV. So we start by platforms strategy. So we can see on the left side of the slide the motor platforms. We have already 2 platforms in place. One with a small diameter, 150. With 8 poles, hairpin until 20 that can run until 20,000 RPM, and after we can scale the length of the active parts that can increase the power of the machine. So with this platform, we can go from 20 kilowatts to 100 kilowatts at 400 volts. On the second, the bigger platform with the 210 millimeters stator diameter. So this one, it's a 6 poles machine with which we can go from 120 kilowatts to 350 kilowatts. So those 2 platforms can cover all the requests or the needs that we have from our different customers. On the inverter, we put the same. So it's something that we developed 2 years after the creation of the GV. So the inverter platform, we have also 2 platforms. One with what we call the E500. So it's IGBT and SiC platform, 400 and 800 volts, and goes to 430 amperes. And we have also one application with MOSFET for ERAD application. And after we have a bigger inverter that we call 1000 that covers also IGBT SiC with 400 volts on the 800 volts and can run with 700 amps. And the last platform that we put in place, so we are at the beginning right now, it's a reducer, so the parallel axis. And today we are from 8 to 15 ratio, and we'll see later on how it will increase. So here the strategy that we put in place at Motors, it's a platform strategy. Target clearly is to reduce the costs, reduce also the diversity at the manufacturing side, and after also to make it easy for the plants to produce machines with only changing the length of the active parts or the current that we can use on the different applications on the inverter. This slide is already the, let's say, applications that we have on the road. So today we cover already 10 brands that we can see on the chart with 38 models. So we have applications for 80 kilowatts already in place until 200 kilowatts. The strategy that we are putting in place for the next generation. So today we can see that we cover all the needs from our customers. The main topic today clearly is the costs of the machines, and it's what also we have seen on the previous documentations that have been presented this afternoon. So what we put in place, the strategy is in 3 points. First one is the downsizing of the machines. Target is to reduce the cost by increasing the speed. We can see in this small chart is that today in motors we are on the bench of the high speed motors, but we can see also the competitors are continuing to increase the speed of the motors. On target for us, it's also to continue to increase the speed. This increase also some critical points on the mechanical aspects. So when we are working today on those aspects, target with that, it's clearly for one application. For if I take an example, M2 Gen 1, it's one application that it's around 80 kilowatts to have the same performance, but so 70 to 80 kilowatts, but with a lower cost. So increasing the speeds allows us to reduce the length of the active parts and to reduce the cost of the final machine. So target today for the next generation of all motors, all products, is to increase the speed and to reduce the cost of the BOM of the different machines that we have already on the field. That is one action that we have in place. The second one is to be ready if tomorrow, as we have seen on the past, there was a diesel bashing. So we don't know if tomorrow it will happen for the magnets. So we need to be ready for that. So customers tomorrow could avoid to buy some machines with magnets. So we developed also internally an electrical excited motor. So today we have already the prototypes running. So we are ready to have also this kind of applications to cover the need of our different customers. The third point is to increase the torque density. So with disruptive technology, this one is clearly the axial flux motor. And this is the topic, the today topic. And so that it's thanks to a Maxima project, we have started also this work, and we'll have in the next weeks and months some prototypes running at home with this kind of architecture. After, in parallel of it, we are working also on some levers. So target, as I said before, is to have a product process with a very low diversity. So we are working to have inverters that can afford 400 volts, but also 800 volts, CKGBT. So it's what we are working to minimize the diversity or to minimize the impact on the process at the manufacturing plant. So it's one lever. We have a team working on that. Topic that we are also working and to introduce on the next iteration is the continuous widening. This one, it's clearly to reduce the manufacturing costs, to reduce the soldering, the time of the soldering, and also the quantity of copper, so that it's an activity that should be ready also for the next generation. At the control side, we are working also on the optimized pulse pattern. So it's a work that we have engaged some months ago. And today we are clearly at the middle of this development, and we will see when we can also reach one application that will go after in the field. Oil-cooled is something that it's not new. We have made some prototypes at home, but we can see that at this level there is a lot of things also to do and to optimize with this kind of technology to cool the machines. So it's clearly a lever for the next generation on which we are, let's say, improving all the things that we have already done on this kind of cooling. And one topic that we have also on the table, it's the laminations. So today we are with the stamping laminations. We try to work also with some improvements that we can do on the stator. So one lever is to have the laminations glued. It's one lever. We have also the slinky, can be also an alternative for the stator to reduce the scraps when we made the part. So all these levers that we are working separately. After, the target is to have it in one of the applicative products that we'll have in the next generation of our products. To make the sum up of our roadmap, clearly it's to make electric mobility accessible for everybody on the market and to cover all the market. That's the target. That's why we are working on the platforms. That's why we are also developing electrical machine rotor. And also we are working today with Maxima with AXIal flux. The second point is also to cover on that. We can see on the field that the request is for BEV, for PHEV, MHEV, HEV. So there is a lot of applications, and to avoid the diversity, because diversity, as we know, it's cost on bill of materials, but also on assembly line, on the process. So we continue to develop the platform. So that's why the target is to continue to improve our platform. So from the 25 kilowatts to 300 kilowatts. So today we have the two platforms motor, the two platforms inverter, and one software on the two reducer. We think today that with those platforms we can cover 90% of the market that we have as a target. And the last point is ensuring market sustainability with the three main topics. Manufacturing cost, clearly it's one lever. We can see that we don't have, let's say, a lot of years behind us as thermal engines. So there is a lot of to do on that topic. So we are working with manufacturing and the suppliers to reduce the impact of the cost to assembly and to build the machines. After the resources on the material, clearly the strategy on the platform, it's one lever that can reduce the material that we can put on the machines for the same performance, as we can see, as we have seen before, increasing the speed of the machine and so on. It's a lever. We have made already some tests, and we have good correlations with what we have made as virtual analysis. And after innovation, we are from my point of view, we are at the beginning of the story for the BEV or the hybridization of the vehicles. So a lot of innovations are on the field, are arriving. We are working on some of them. So clearly is to make our platforms to evaluate on the next months, next years. We integrating those innovations. Target at the end will be always the same: less cost of the machine, a better price, and cover all the needs of the different customers that we can have. So that's the synthesis of what we can see after 6 years of having e-motors already on the market.
Thank you very much, Gilles, for the presentation. So what I propose to do is to have time for questions. So is there some questions? The attendance? Yes, Hamid?
I have a small question about the Slinky process. So you referred to Slinky. We know the Slinky will introduce kind of stresses during the production, which will affect the efficiency of the motor. Can you say something about this, please?
Yeah, in fact, it's the trade-off we are evaluating that today. Yeah? We have some prototypes that will run in the next. It's before summer. Target for us is to see what we can obtain as a target price of the parts and what we can save as cost. In front of it, we'll have some additional losses that we don't have today. So target at the end is to make a balance between what we can lose as efficiency in front of what we can save as costs. And we think that at the end we could have some applications that Slinky could be a solution for our customers. But you're right. I agree with your comment.
And this is for which type of vehicles? It's for a hybrid electric vehicle or for a battery electric vehicle, if I can ask?
Battery electric vehicle.
So it's really cost-driven. It's not efficiency. This is.
Sorry.
This is cost-driven now. It's not efficiency-driven. I mean.
Both, because in fact, efficiency at the end is a cost, because from the EOM, when we are losing efficiency or when we are improving the efficiency, in fact, the EOM, in front of it, they put what it costs of equivalent of battery.
Yes, indeed. Yeah.
So at the end, it will finish the cost versus cost.
Okay, thanks.
You're welcome.
Other questions or remarks? So maybe I have one. So related to innovation and challenges, what is your opinion about where we should put the effort? It will be on the magnetic part, structure, or on the thermal system of cooling, or on the mechanical part? what would be, in your opinion, the main challenge? Magnetic, thermal, or mechanical?
Now, mechanical, I don't think so at this stage. With the radial motor that we have, it will be clearly a topic for the axial flux, as we have seen in the previous presentation. But at this stage, what I think is that it will be on thermal, on electromagnetic side. Clearly, more we can improve the cooling of the system, more we can reduce the size of the machine. And if we reduce the size of the machine, at the end, it will finish by reducing the cost of the final product to the customer.
Okay. Another question?
I have a question, Gilles. Abdou from A Motors. Yes, I have a question about axial flux machine. So we talked about Maxima. So Maxima project is principally for battery electric vehicle. But do E-Motors think about that axial flux machine can be but can be interesting for hybrid and plug-in hybrid electric cars? What do you think about?
It's something that we already talked internally. Here today, the target with Maxima, clearly for us, it's to have a clear status at the end. With that status, because there is the process that it will be a big topic, as you have shown previously. But in fact, at the end, I will be, I think, I'm quite convinced that will be an architecture that can be used for both. Because in fact, it will be very thin. The packaging will be interesting to have it also for hybrid.
Okay. Ahmed, again?
Yes, I'm again. I have a question related to you mentioned for innovation. What we see now from the market, you see Xiaomi motor, they target 27,000 RPM and they are going to 35,000 RPM utilizing the rotor mechanical strengths are about 960 megapascal yield strength. What is your feedback about this?
Alors, we are clearly in the project that we opened some months ago. Clearly for us, it's to reach about 30,000 RPM. We need to go through that. Today we have applications on the road with 20,000 RPM. We have prototype products that can run until 25 or 26 RPM. We are working internally today to reach around 30,000 RPM, but we need to go with higher speed. So that's clearly the first point that I put on the slide is to increase the speed of the machines. It's a lever that I think a lot of companies like us that make the machines will go at the end. From today, we know that we have a good product on the field with a very high speed comparison to the others. But if we do nothing, the others are increasing the speed. We know that it's a lever. So until at least 30,000, we can reach it. Okay, it will be. There is some challenge, mechanical challenge, as you mentioned, but it's something that we can reach, and it will be interesting for the radial architecture.
We have to start. So Gilles, thank you very much for your presentation and the answer of your question.
Thanks a lot.
So after being on the road, now we will go in the air. Okay. So I don't know, Christophe, you are with us?
We cannot hear you, Christophe.
I open my microphone. Do you hear me?
Yes, but you are far away. You are high in the air?
Not really. I'm on the ground.
Okay, we can see you, so that's. But we can hear you also. That's okay. So.
Okay, so do you really hear me?
Yes. So I will introduce you, Christophe. So Christophe Viguier from. So he's working at Safran-Tech. He's the leader of the electrical machine team. So, Christophe, the floor is yours.
Thank you, Stéphane. Do you see my presentation also?
Yes, and you too. So that's good.
Okay, perfect. So sorry, Jean-Frédéric, change the slot in between us. I have some constraints afterwards. So the objective of my presentation is to share with you some insights on the stakes and challenges of electrical machines in aeronautics. I will not go into technical details. The idea is just to share with you some overview on information and figures related to our product and the production. So first of all, if I can switch, okay. Let me just explain what are the challenges of the decarbonation in aerospace. So some international organizations define a roadmap to achieve a net zero emission in 2050 compared to 2015 CO2 emissions. And for that, we define four main axes. Thank you for the time. We define four main axes and thematics to investigate. So the first one is dedicated to the technological progress from the aircraft definitions up to the subsystem, up to the equipment. So that's where electrical machines were involved. Another aspect is to optimize the traffic management. I will not go into details. The major part is dedicated to the use of sustainable aviation fuels, 50% of that. And the last one is just an offset to reduce the net emission. So based on this roadmap, Safran developed a technological roadmap with three main pillars. The first one is dedicated to the concept, the design of ultra-efficient propulsion system, meaning ultra-efficient turbo machine, turbofan. The second one, for sure, is the use of sustainable aviation fuel, taking into account also some hydrogen propulsion chain, but this is something much in a longer time. And finally, the third pillar is dedicated to the use of electrical machine for electrification of the propulsion and also for the hybridization. So it's quite new for aeronautic. It's older for automotive. Thus, so we have a lot of challenge and stakes with this kind of objectives. So to increase the maturity of the technology, we define a progressive roadmap with a progressive applications for the electrification and hybridization. So the date is just to have an idea of what will be the target, but this is something that can change in with 5 years or in 10 years. So the main thing is that we start with the generalization with about 100 kilowatt installed in the aircraft. So this is for the full electric aircraft, up to another platform like the VTOL, electrical helicopter, let's say, and the commuter, the small aircraft with less than 20 passengers, with an increase in power in between 250 kilowatt up to 500 kilowatt. And afterwards, we can think about other hybridization or distributed propulsion for regional aircraft like the ATR-42 or the short and medium range like the A320. So in this kind of architecture, we can think about 1 megawatt installed in the aircraft. So with the increase in power, there is also an increase of voltage to limit the current and so to limit the size of other components like protection, wire, and so on. So for this kind of application, we think about a limitation of the voltage up to 1 kilowatt, 1 DC kilowatt. Afterwards, this is now a long-term vision, a long-term objective. We can think about new relay aircraft with much power integrated up to 10 megawatts. This is something very long-term again. And for this kind of application, we can think about new breakthrough technology like superconductivity, cryogenic, and so on, and other aspects. So for this kind of application, maybe we will need to go over above 1 kilowatt, but this is something very, very long. Just a remark, in this roadmap, there is no consideration of hydrogen perspectives. It can be included in some example. So regarding the electrical machine perimeters, with these new challenges, there is a new application compared to legacy aircraft. Up to today, the only high power, let's say, electrical machine installed in an aircraft is a generator. But with this new architecture, there is new electrical architecture with this new aircraft concept series, there is new HVDC architecture and new need in generation. Even the generation will increase and will be very challenging. There is also that we call the more electric aircraft. This is actually the replacement of the hydraulic function by electric function. For instance, the flight control with electromechanical actuator, the taxiing of the aircraft by an electrical machine installed in the wheel, and other non-propulsive functions. The main topics really that challenge us is the more electric propulsion. So the idea is to replace a thermodynamic propeller by an electric machine, so a NIPROP, electric propeller, or an electric fan, depending on the aircraft platform. And finally, the last one is the hybridization, like in automotive. This is the full electric in this way, and this is the hybridization in this way. When we put some electrical power in addition of thermodynamic power, even for turbofan, so for an A320, a turboprop, AXIal, or for a turboshaft, this is for an helicopter. This is something very interesting. And close to this, I think, in parallel with these new applications, there is also an increase in requirements and needs. So in terms of power generation, we want to go from 200 kilowatt up to the megawatt class. This is quite new in aeronautics. This is the same things for the shaft mechanical power, for the propulsion, electric propulsion. We want to go from 100 kilowatt up to the megawatt class. And with this increase of voltage, like I already said, there is also an increase in voltage. Today is close to an equivalent of 270 DC voltage. We want to go to 540 DC, 800 DC, and maybe 1 kilowatt. And the major point, that the main difference with the other application, like you said, Stefan, we are in the air, so we have some aeronautical constraints. The main ones is the altitude, and with the altitude, this is the low pressure and the temperature. When I say altitude, I said also some problem with the high voltage, like partial discharge. That we have to manage. It's more important for automotive application for sure. We speak about also cosmic radiation for the power electronics and so on. So this is really some constraint higher than the other application in aeronautic. And the last one is the safety requirements. We used to say that in aerospace, safety first. So our devices and our equipment have to be safe in a way. So that's why we need to develop a lot of new machine with high power, high efficiency, a lot of high something like I put on this slide. Okay. I will continue just by sharing with you some example of high power application. This is like a state of the art. The idea is to show you what are the much mature devices with mature technologies also close to already flight or in the coming years. So historically, the first one, like I already said, is the electrical generation. The first family is what we call a variable frequency generator. This is actually a three-stage electrical machine, one feed synchronous machine plus a PMG. This is something very usual for us, with a range of power in between 100 to 250 kVA and an operating range in between 10 and 25 kilo RPM. So the VFG is a variable frequency because the speed of the turbofan varying during the flight from the idle to the cruise speed in between these two speeds. So the generator have to provide the power in between these two speeds. You have some example here, and this is something very robust and very interesting because we can manage the flux of the rotor by the generator control unit. In case of fault, you can intrinsically and basically have a flux weakening, a native flux weakening. The inconvenience of this, the drawback of this application is the power, specific power, very low compared to what we want to go if we increase the power. So the second family is for the turbo generator. The turbo generator, we plug a generator at the output of a gas turbine. So it's like a compressor. The idea at the end is to provide a power at a constant speed. So for this kind of application, we want to go higher in the power generation from 300 kilowatt up to the megawatt class. And we want also to go higher in terms of rotational speed because we are connected directly to the gas turbine, and the gas turbine operates at high speed rotation, high rotational speed. So you have some example here of two technology, a PMG, a permanent magnetic generator, and also a wound-feed synchronous generator with two different rotational speed, but with the same, let's say, specific power and efficiency. This is very high for this kind of machine. The other application is the electrical propulsion. The electrical propulsion, I propose to distinguish two families. The first one is the radar topology. The second one is the AXIal topology, to do a link with the Maxima project, for sure. Historically, the radar topology is much investigated, is more investigated in aerospace because due to the shape factor and the maturity of the technology in a way. Regarding the electrical propulsion, for this kind of topology, the radar topology, we think about power range from 100 to the megawatt class, again, but with low speed, in between 1 to 3 kilo RPM. Up to now, the architecture used in this kind of application is a direct drive architecture, meaning there is no gearbox in between the propeller and the electrical machine. That's why the electrical machine is also a low-speed machine and high-torque machine. For this kind of machine, even if I speak in specific power, 5 kilowatt per kilogram, I can speak also in terms of torque to ratio or mass ratio, or torque to mass ratio, sorry. And we achieve something about 20 and 30 meter-newton per kilograms. You have some example in this slide. The first one, not because I am from Safran, but this is a story also, is a 120 kilowatt, 28 kilowatt with the first type certification delivered by the EASA. That this is the first electrical machine with this certification. We know that some competitors like Zeroavia and Magnix that are well mature in some technology are close to the qualification certification. So with other entity, FAA and other, and they develop some concept about 600 kilowatt and 2.5 kilo RPM. So you can see maybe this is a system very compact, very minimized in terms of volume, with a lot of electronics because there is a lot of segregation in the different phase of the machines. And this is something for this Enginous 100. The power electronics is integrated inside the close to the electrical machine to limit the DVCDT, the MC filter, and so on. So we want to and we work to minimize really the integration and the volume and the mass of all the system. And about the axial topology, this is quite new in aerospace. Let's say compared to maybe to other applications. Some years ago, 3 years or 4 years ago, something like that, there is the first axial machine integrated in a training aircraft. This is the MRAT. This is also a permanent magnetic synchronous machine. And we know that the former EASA company created Evolito for aircraft, and Evolito is developing also an axial flux machine with lower power than the other one, not the megawatt class, but some hundreds of kilowatts. But the specific power is less interesting on our side. This is maybe something to discuss for the future. And to finalize my presentation in terms of what are really the main KDDs, the main key design driver for electrical machine. This is not in priority order. This is just the main 5 main points. For sure, this is a specific power. We have to reduce the weight to limit the consumption and to limit the drag of the aircraft, or the aircraft, sorry. And this is a double penalty for an aircraft compared to a car. So for that, we use high performance materials. We use also highly efficient cooling. We try to push the limit of the air cooling device for maintenance and cost reasons, but at a certain point, this is necessary to go to liquid cooling options. And for that, we have also a lot of experience on that. And also, we try to limit the ferromagnetic path by increasing the number of poles, so the high frequency of the electrical machine, but in close relation with the power electronics. This is always something very interesting. When I say high performance material, we use some iron cobalt, some iron cobalt also for permanent magnet, and so for the insulation, we try to go to the higher class, thermal class for all these materials. In terms of efficiency, this is not quite new, but it was at the beginning the second priority. Now this is also a first priority because there is some impacts on the source for sure, but also on the TMS. The TMS is a thermal management system. So if we want to optimize the overall system, this is an holistic approach. We have to take into account also these parameters, the efficiency. Another difference is the lifetime. For an aircraft, the lifespan is very long, in between 25 and 30 years, meaning in between 40 and 60,000 flight hours. So this is something very challenging for us, compared maybe to other applications, and we have to go with that. So if we want to increase, for instance, the voltage and to control, to limit the inception of partial discharge, we have to take into account also that, and health monitoring and so on. And safety, like I already said, safety is first in aeronautics, so we have to take into account the quality and the robustness of our product, and this is something very well known on our company and in our applications. Some of the works are already done only. So maybe if we want to go on other aspects, we have to think about automatization. So this is something that we have to emphasize with the cost. And again, the aeronautical environment is quite constrained for us. And the last point is the cost. There is a new paradigm because there is an increase in demands. So, like you said in the beginning of my presentation, there is new use cases with new applications. So, meaning another quantity to produce of electrical machines quite different that we have today. So we have to think about the next step of the industrialization and the manufacturing also. This is something already, let's say, integrated in automotive, and we have maybe to find some inspiration from your manner to integrate that in our industrialization. So to conclude, for the first step, our current products are at, let's say, at the top of the state of the art regarding the maturity of the technology and the competitive performances. For the next step, if we want to go further, we need to push some limits with some technological breakthrough, and also taking into account eco-design. We use some rare earth material. If tomorrow we will not access to that, what will be the technology? And we are working on that. So that's all for my presentation.
Thank you very much. We have time for questions. Is there questions? Yes, Jean-Frédéric?
So hello Christophe, it's Jean-Frédéric. So I have a question for you. In fact, you have speak of the airplane, but what about new kinds of aircraft? I think of unmanned vehicles, drones, and so on. What about the challenge about the electrical machine for this kind of vehicles?
So, when you speak about unmanned air mobility and other aircraft concept, this is on my second slide, explained by the VTOL. This one, yes, thank you for the sharing. This kind of platform will be for us the first step of the demonstration of the technology that we are developing.
Yes, of course.
For this kind of structure, the maximum power is in between 100 to 250 installed in the concept, meaning that for one electrical machine, it's in between 50 to 100 kilowatts. So we have today the product, the technology to integrate in this kind of architecture, and it can be a first step to validate the technology.
Perhaps it is more easy in this kind of system to have an innovative approach because it is a smaller system, in fact. The systems are smaller,
Right,
so you can experiment more, perhaps.
Yeah, we can experiment a lot of things with the generation, with the VTOL, with also the commuter. This is that are the smaller platform with a certain level of power really manageable. We can test a lot of things, but at a certain level of altitude.
Yeah.
And for the next step, just to give you an example, the general aviation is between 10 and 15 kilofeet in altitude.
Yeah.
The regional is in between 25 and 30 kilofeet. And the SMR is in between 40 to 50 kilofeet. And with this increase in altitude, a lot of problems can occur.
Okay.
Not problem, but new challenges.
Okay. Thank you very much, and thank you for your presentation, which is very, very interesting. So, thank you.
Pleasure.
So our online audience is very quiet, but maybe we have another question in the room.
I have one at least.
Okay,
At
so
least
Stefan.
one. I have several, but just as you said, Christophe, the reliability or the safety is very important. So how do you take this into account during the design of the electrical machine?
So there is different approach and different requirements, let's say. The first one is at the aircraft level, there is an analysis with the functional hazardous analysis to define what will be the need in terms of number of channel, the needs in terms of MTBF, reliability, and so on. So for us, it is the first step to define if we need, for instance, one channel, two channels, and other aspects. But this is one way. The other one is to mature our technologies with agile test and ACT test, accelerating test, to validate some models and results that we record. And the last one is maybe if we don't have enough information, is to think about health monitoring. And there is a really huge challenge in health monitoring in the aircraft.
Okay. Is there other questions or Mark? Yeah.
Last question, sorry.
No problem.
So from Abdu from eMotors, I have a technical question possible. You talk about a generator near than the gas turbine, if I know. These don't have to. If I don't know if this is conventional generator, and if yes, this is I think that have risk of partial discharge in terms of temperature, so near than gas turbine. And two, high speed. And I see that you talked about winding rotor, so wind rotor. So it's complicated for me to understand all these constraints, but I don't know if it's how you manage this.
So when I speak about turbo generator, you have on the side is a gas turbine, and with the exhaust on the side. So the exhaust is the output of the high temperature thrust. Okay. Yeah, on the other side, so in a cold side, we have the generator. So there is no direct impact of temperature. The main thing is altitude, always with us. I think I answered the first part of the question, and I don't remember the second one, sorry.
The second about speed.
Yes.
Speed and the winding rotor.
Yeah. So historically, we have the VFG, which is composed of boom rotor, like the EESM, for instance, that the previous speaker presented in one slide. And there is, let's say, 30 years of experiences to fly this kind of component in this range of speed. So we master a lot of things with one rotor, but up to 25 and up to 200 kVA. If we want to go in higher power, in higher speed, this is another question. That's why we change maybe of technology, and we will go. I think we are going to the machine.
Okay, thank you.
My pleasure.
So thank you very much, Christophe, for your. And I think we will release you on time. Okay.
Thank you.
So thank you very much again. And so we will switch to the next and the last presentation. So now we will go on the ocean with Jean-Frédéric Charpentier from Naval Academy.
Yes, okay. So it is not...
it's
okay.
not.
Perhaps I have something to do with it. Attends, vas-y, essaie de passer le plein écran. Attends, CTRL-L.
Ah oui, c'est du...
Ouais, c'est du PDF, pour ça j'étais trop lourd.
CTRL-L.
Ok, no, not good. Ok, c'est mal barré là. Attends, vas-y. It is a PDF one. Full screen. Full screen, yeah. J'aurais pas dû faire un PDF. Voilà.
Oui.
Non, c'est pas bon. Voilà. Okay, thank you very much. So, so good evening. Buenas tardes. So my speech will be high-performance electrical machine on drive for marine propulsion. So now we are, as said Stefan, in the ocean, so it is another contrast. So I will try to present this. So first of all, I will speak a little about the evolution of propulsion and the trend to electrical propulsion. So in classical, traditional
Vous avez les flèches pour changer.
Okay.
Et ne pas bouger.
Ah, okay. I don't have to move. Okay. If you could, in conventional propulsion system, you have classically the internal combustion engine, which are directly connected to the propeller, and the propeller are variable pitch propeller because it is not possible to use the diesel at very low speed. When your ship, it has very low speed, of course, your propeller, it has very low speed, so it is not possible to have the diesel. It is why here there is a variable pitch propeller. And here you have a gearbox, but this gearbox have of course, a fixed ratio. That means that in a traditional propulsion system, you have directly the diesel, which is connected to the propeller, and the operating point of the diesel depends strongly of the speed of the ship. So that means if you use the ship at low speed, you will use the diesel at very low power, so it's not very good. So it is why progressively from 30 years, there is an evolution toward electrical propulsion. So in an electrical propulsion system, classically, you will have a set of diesel generator or gas turbine generator which supply by an AC grid. So the system is really powerful, up to 100 megawatt, 10 to 100 megawatt. So that means that this AC grid is typically 4 to 11 kilovolt. 60 hertz, and then this set of generator will supply this grid in energy, and then in this grid you have the load which are connected, and the load includes the propulsion system, and classically the propulsion system are variable speed machine and drive with here fixed pitch propeller which lead to a better efficiency of the propeller because, of course, the electrical machine and drive can be used at very low speed. It is not the case of the engine. So with this configuration, the operating point of the propeller and the sources are fully dissociated. That means that you have a lot here of sources. That means that you can optimize, in fact, the number of sources on and their operating point and the propeller operating point. And so the fuel consumption and the emission are minimized due to the degree of freedom related to the number of sources, in fact, we are shared in the AC grid. So this kind of system allows also supplementary degree of freedom in naval architecture because you can eliminate a large part of the shaft and so on. For example, you can put the engine room in other place than in traditional propulsion system. So because the electrical cable and so on are not constrained in terms of geometrical disposition. And this is not the case of a shaft, of course. And so it allows to imagine a new naval architecture thanks to this kind of integration. Also, it leads to discretion because you have the electrical motors which are more discrete than internal combustion engine, and progressively in this kind of system there is integration. There is a trend to integrate a new generation of sources, for example, energy storage sources, fuel cell, and renewable energy. Renewable energy only for a limited part because of course the ship is very powerful, more than 10 megawatts. So even if you put some PV, for example, in the deck, it is only a very, very short part of the power which can be provided by these renewable energy sources. And it allows also to implement hybridization solution like here, for example, here this is a solution, for example, where there is an internal combustion engine, for example, a gas turbine, which is associated with the propulsion motor. That means that, for example, you will use the gas turbine for very high speed, okay, to provide very high power because the power is approximately proportional to the cube of the speed. So for example, if you have a frigate, the average speed is about 50 knots, but the maximal speed will be about 30 knots. So that means that you have a rapport 8 between the power needed for 50 knots, which is the average power, and the power needed for 30 knots. So that means that this is a good solution to have a very powerful combustion engine to connect, to cross-connect to the shaft of the propeller. There is also evolution of the grid toward HVDC grid and what is called zonal grid. Zonal grid means you have several zones on the grid with several levels of frequency and voltage, and these zones are interconnected with converters which allow to manage very, very precisely the exchange of power between the several parts of the grid. So this is the context of the electrical propulsion. So, okay. So the electrical propulsion allows also to implement a specific propeller. For example, one of the most popular solution for propeller, for electrical propeller, it was called a pod system. In a pod system, you have the pod include all the elements of the transmission of the motor to propeller transmission, so the motor, the shaft, the bearing, and so on, and also the element relative to the maneuvering of the ship. That means the steering gear and the rudder. So in fact, in this system, the motor is located in an azimuthal nacelle, which is located outside the hull. That means that you can rotate the nacelle and very quickly orientate the flux of water, which leads to a very strong improvement in terms of maneuverability. Okay, so it is why this solution is very popular. Also, it allows to eliminate the shaft, so it gives supplementary degree of freedom in naval architecture. For example, in this figure, you can see the association between three pods. Two of one are tracting pod, so they are put in the opposite direction as traditional propeller, and the third one is pushing pod, which operate as a traditional propeller. So this configuration, for example, allow to optimize the hydrodynamic efficiency of the propulsion, and also to optimize the hull shape and to be more efficient. It is an holistic approach, if you want, to be more efficient for the propulsion system. The pod can be also used in combination with more classical onboard motor. For example, here you have a traditional propulsion made by a diver, and here there is another propeller in a pod which rotates in the opposite direction as the main propeller. It allows to increase significantly the efficiency of the propulsion system, and also to increase the reliability. So if you consider this kind of system, of course, the system are very powerful, up to 22 megawatt by unit. For example, it is the higher power pod you can find, and very low speed, about 100 to 200 RPM. Higher the diameter of the propeller is, lower the speed of the propeller is, because in fact the propeller speed is limited by the tip speed rate at the end of the blade of the propeller. So it is, of course, so it leads to very high torque. In fact, more than it is. The torque are in the meganewton meter range. So the machine are very, very high torque. So it is why probably you know that at first order the volume, if you fix the technology, the volume of an electrical machine is directly related to the torque. Okay, so that means that it is really a challenging point in terms of integration. You see here, for example, the volume of the nacelle where the motor is. The volume of the nacelle is very huge. Okay, so it is not so obvious to integrate the motor with the pod, for example, but it is also true for inboard direct drive system. It is a challenge in terms of capacity. So the advantage of electrical propulsion have led that electrical propulsion has become a standard for a large variety of vessels, which use ICE electric system or electric hybrid system. So it corresponds to a large range of mission profile, specification and content with several categories. For example, this is a standard for passenger ship. For example, the passenger ship which are built, for example, by the Chantier of Saint-Nazaire, for example, in France, are all with electrical propulsion. Scientific ship, it is very interesting to have a very silent mode or a non-intrusive mode, for example, for the measurement. LNG tanker, where you can boil the excedent of natural gas, for example, to provide electricity. Tugs, which are characterized by a very high, very various mission profile in terms of power. Moving platform means that you have a platform with propeller and you use what is called the dynamic positioning. You use the propeller to position dynamically in real time the platform, for example, for drill or this sort of thing. Okay, so in this case, it is not really a ship, but it is a platform with propeller, in fact. And the platform is not moored in this case. Okay, it is free, in fact. And of course, military vessels, surface warship, for example, this frigate use an hybrid electrical gas turbine, diesel electrical gas turbine propulsion, and also submarine, because in submarine, for example, if you want to have a sealant diving mode, so for example, if you use the battery electrical propulsion or fuel cell electrical propulsion, it can be an interesting solution to have a very sealant mode where you are in diving operation, a very discrete one. So what are the main challenge for, even if there is a large spectrum of our vessel, it is possible to exhibit some common challenge for maritime propulsion motor. So the first one is the redundancy and the reliability, because when you are in the middle of the ocean, it is not so easy to have a phone call and say, okay, I want, can you send me a team to repair the ship? Not really easy. So classically, it is a need to have highly reliable technologies, and also to use to have technology which allow for some fault-tolerant modes. Another challenge, as I have already speak a little about that, is the capacity. So you can see here some classical value. So this value perhaps appear to you very big. For example, the 25 Newton met by kilogram. But in fact, the value depends of the radius, depends of the diameter of the machine. Here we are with machine with a large radius, low speed, so there are a lot of poles. So in fact, the machine are like a ring, in fact. Okay? The center of the machine is free of active part. Okay? So that means that more the radius is high, more the force which are exerted in a large radius, so the capacity increases strongly with the diameter and the radius. So this is why this value can be reached, in fact, because in fact the motors are large in terms of diameter. So of course the efficiency. Another challenge is the integration with the propeller. The idea is to try to find some solution to have a holistic integration of the propeller with the motor, as in the rim-driven system. I will speak a little about that just after. Of course, all acoustic behavior and vibration, particularly relevant for military application, but also for civilian application. For example, if you consider a passenger ship, of course, you don't want to have the vibration in the passenger cabins, okay? So it is one of the more difficult things to have a very low level of noise in the passenger cabins. So of course, the acoustic behavior is really an important criteria. And becoming more and more important is like in all the sectors, the life cycle analysis and impact. I have read, but I am not an expert, that 80% of the impact are related to the operation, and only 20% for the fabrication and the dismantling. Okay. So just a few. This is. I cannot present all the cutting-edge technology, but some of the more important. The first one is what is called rim-driven propeller. In a rim-driven propeller, the electrical propulsion motor is located in a nozzle which surrounds the propeller. So the motor is fully integrated with the propeller. So the blade, in fact, are the rotor of the motor. Support the rotor of the motor. So it is really interesting in terms of capacity, because you increase the diameter, as I said previously, it leads to a better capacity. It is also interesting in terms of hydrodynamic efficiency and acoustic behavior, thanks to the ducted propeller, which allow to have a better characteristic for this topic. This system is also suitable for pod system, as you can see here. And this system also facilitates the unconventional propeller implementation, because it is possible to avoid the shaft as here, for example, so or here the shaft is avoid. So for example, you can use two motors with two propellers. One rotate in one sense and the other rotate in the other sense to improve the efficiency of the propulsion. So of course, this kind of propeller needs to have a multidisciplinary approach because the design is a compromise because the hydrodynamic characteristics, the thermal characteristics, il faut que j'accélère. The thermal characteristics, the mechanical, and so on. So like in the Maxima project, it is need to have a multidisciplinary approach. So another way to improve the performance of electrical motors is to use unconventional machine structure. So there is several unconventional machine structure which can be used for marine propulsion motor, vernier machine and so on, but I will speak of course of axial flux machine because I will speak to Maxima. Axial flux machine is one of the promising track. It allows to increase the redundancy and the modularity with several possible magnetically independent stator. The capacity can be higher. So it is due to the increase of the gap surface and possible coreless solution. And also it is possible to have specific integration with control rotating propellers or redriven propellers. For example, here is a study where we compare, for example, a radial flux permanent magnet machine with an axial flux one in a ring-driven propeller for 2.1 megawatt, 105 ERPM. But of course, there is a challenging point. You have seen that in the Maxima project about the mechanical stability and the thermal behavior. And also, of course, there is a need of a fast and holistic multidisciplinary modeling and design approach. So another cutting-edge technology we work a lot in this technology is to use what is called multi-phase machine and drive. Multi-phase machine and drive means that you use more than three phases, or you use several three-phase winding on the motor. For example, here you use several three-phase winding. For example, each motor has 4 three-phase winding, and here, for example, you have 9 phases in the motor, and here you have I cannot say you exactly the number, around 10 phases, and with an independent averter for each phase. So this kind of system allows to increase the redundancy because it allows to have a fault-tolerant operation. It allows also to improve the acoustic behavior and reduce the constraints of the component. For example, if you have a 21 megawatt motor, for example, motor and drive, if you have, for example, 3 phase, you will have 7 megawatt by phase, so it is not so obvious in the averter point of view. If you have a 7 phase, you will go to 3 megawatt by phase, and if you have a 21 phase, of course, you will go to 1 megawatt by phase. So it is more easy to manage, for example, the quality of the current and the torque. And so these systems are really interesting for marine propulsion motor, but the challenge is managing the complexity between all these phases. So there is need to define a devoted modeling, control, and design method. In our lab, we work with the fictive machine theory, which has been developed in L2EP with the team of Eric Semai. And also a challenging point is the reliability, because when you increase the number of phases or number of circuits, you increase the possibility of reconfiguration, but you increase the number of components, so you increase the probability to have fault. So there is a compromise between the complexity of the system and the possibility of reconfiguration you have. So there is a lot of work to do on this topic, of course. And the last technology I will speak about is about the use of high temperature superconductor. So the idea is to use high temperature superconductor classically to main the field winding of a synchronous motor. So it allows to increase the magnetic flux density and so the tangential shear stress, And so to increase the capacity, you can see here, for example, a 36.5 megawatt motor at 120 RPM. So this is a conventional design, and this is, for example, an HTS design. Okay, so you can see the gain of capacity. It is this machine has been built by the Society American Superconductor. So of course the challenge in such machine is cooling the HTS, is to have no quench in the superconductor, and also there is challenge about mechanical system because there is no core, in fact. So that means it is not so obvious because the force is exerted directly on the coil, so it is not so easy. So I have finished my presentation, and I will conclude. So in fact, the maritime propulsion leads to specific and severe constraints. So there are a few cutting-edge technology which are under deployment to face this challenging goal. But they need to develop, like in the Maxima project, a specific multidisciplinary approach for the design of this new generation of maritime propulsion motor. And just a few words about the new challenge which are coming, which will deal with the autonomous vehicles. For example, this vehicle, you know, this is an autonomous underwater vehicle. For example, it is an autonomous submarine, if you want, with specific constraint. And I have finished, so sorry for for the time.
Any questions in the room? We have.
Yes, I would have a question regarding the materials. You mentioned permanent magnets. Yeah. Do you use neodymium iron boron magnets or samarium cobalt? Do you know that?
Okay. For military application, the samarium cobalt are more used.
Okay, because of the higher application temperature, yeah, probably. Yeah. Okay. And do you know...
neodymium are more used for civilian one.
Okay. And do you know the amount that is used for such huge motors? Probably in the ton range?
Yes, the ton range.
Okay. So it's also maybe relevant for recycling then?
Yeah. But perhaps, you know, it is very near, for example, of a permanent magnet generator for wind turbine or this sort. It is not so different. For example, if you consider a megawatt range wind turbine, you have also a megawatt, a mega Newton meter range for the torque. So in fact, you will have quite the same volume of materials and so on.
Okay, thanks.
Of course.
Question about you talked about the fault tolerance.
Okay.
Yes. How we can think about fault tolerance in this electric machine in operating range?
Je peux, moyen de partager. Can you share? Okay, for example, here fault tolerance for multi-phase machine. Here, for example, you lost one phase, yes, and then you can continue to rotate the machine with the LC1. So you disconnect this phase, but with here you have 5 phases, for example, and with in fact, you need only 3 phases to rotate the machine. You need only 3. In fact, you need 2 phases. But with the connection, you lost 1 degree of freedom. So with 3 phases, you can make your rotating field. So for example, in this 5-phase machine, I can lose 2 phases and continue to operate the machine. Of course, with the lower torque. Yes. Okay.
And if we have, this is the case. Thank you. Sorry. This is the case with multi.
Ok, excuse me. Je n'ai pas l'habitude, moi.
This is the case of multi-phase motor or system. But if we have 3 phases, it's...
3 phases is more complex, even if the phases are not are supplied by
yes,
by a separate inverter. But with 3 phases, if you lost 1 phase, it is finished.
Okay, so we privilege the multi-phase. Thank you.
It is why this kind of system, but for example, if you consider an axial machine, for example, as yours, with two stator, okay, yours has only one stator. But if you have two stators, for example, you can say, okay, I supply one of the stator by an inverter, the other by a second inverter, and then I can. Of course, there is problem of a balance and so on, mechanical balance, but perhaps I can use it. Okay. And another way, for example, for multi-phase machine is to use, for example, one inverter with two machines by specific connection and to control the two machines in an independent way. So that means that, for example, if you have two 5-phase motor with two 5-phase inverter, you lost one inverter and you connect and you go to this scheme which allow to control the two machines independently. Of course, you will not be able to control it by the same power and the same and so on, but it allows you to continue to use the machine. And also, you can also make a 3-phase machine with several independent windings supplied by several inventors and so on.
Okay, one last question. Anyone? Okay.
I have seen that you commented on thermal issues on the advanced technologies like axial flux machine or high temperature superconductors, but can you give us some feedback about generally in your application, thermal issues are less dominant or less important than, for example, in automotive or aircraft, or because you are in bigger volumes, better surrounded by cold fluid, or are still important?
Yeah. Thermal is, in fact, if you consider the design of a machine in general way, this is firstly, it is a compromise between thermal aspect and electromagnetic aspect. But of course, more big your machine is, more it's difficult to cool it. Because you know the surface to evacuate the losses is proportional to the square of diameter, and the losses are proportional to the cube of the diameter, okay, to the volume of the materials. So that means that if you make a very, very big machine, it is even if the efficiency is very, very good, it is very, very difficult to cool it. Higher the volume of the machine is, more difficult to cool is. You know, it is why, for example, if you consider the big generator for the grid, for example, they have an efficiency of more than 99%, but the cooling aspects are very important. Okay, they are water cooled and so on. Even if the efficiency is more than 99%. So in fact, because we have big machine, thermal aspect is one of the major challenge. Je suis en train d'exploser le temps, là, c'est ça qu'elle dit.
So thank you very much, Jean-Frédéric, for No. So it's time now to conclude. So I will be very short because I suppose that some of you are thirsty. So because a drink is waiting for us outside, not for people online. I'm sorry. So wouldn't be. So first, so what I would like to say is that I would like to. I hope that this midterm conference gives you an idea of what is ongoing in the Maxima project. And also, I would like to thank the last three speakers, so Gilles, Christophe, and Jean-Frédéric, because we can see through their presentations that the ideal electrical machine doesn't exist, and it depends highly on the application. And I think that it's really important to mention that. And so this is the case in the Maxima project, as it was said by Abdou, that we have to choose, for example, a certain number of poles and so on in function of the application and in function of the specification. And this is something that is important and we have to keep in mind. So I don't know, Gilles, if you are still with us, but I would like to thank you for your presentation, and also Jean-Frédéric, and I know that Christophe had a constraint, so had to leave us. And so thank you very much, everyone, and see you for the last meeting we will have in 2 years, so for the end of the Maxima project. Okay, thank you. Bye-bye.